пойдет? Хорошо. Ага. Ага. Понятно. О!
Повторить прошлое, я понял. За кофе сбегать.
Давай, давай.
Там есть. Первый принцип утверждение А и утверждение не А одновременно были бы верны. Кто этот принцип не уважает, уже учет.
Чего? Наверное, кондиционер не включен, я думаю.
Да, у каждого человека список работ.
Угу. Ну что, включили кондиционер? Включили кондиционер? Он вообще, по-моему, выключен. Не дует, по-моему, вообще. По-моему, вообще не выключен. Не включен. Очень жарко, душно.
Вот это надо. Вот это нам надо.
Ну, конечно.
Даже на минуту позже.
Хорошо, хорошо. Что-то ничего не включилось.
Good morning, everyone. Welcome back. And we will start with the second lecture by Professor Andrea Kunkov.
Thank you, thank you, thank you. So maybe we'll start the second lecture with a little more formal discussion. What is cohomology? Cohomology. So first we need some X, which could be maybe a topological space. For instance, among all possible topological spaces, you can look at particularly nice ones, so maybe finite cell complex. Another very nice kind of topological space is a manifold. So this is all possibilities. So for what we're going to do, particularly important are complex manifolds. And if you somehow enlarge your universe of possibilities, you can always even study, this requires a separate discussion, but leads to similar results, you can study also algebraic varieties. Right, and it doesn't have to be over a complex number, over something, over some field, for instance. And so then in this category, you have maps. So for topological spaces, these are continuous maps. And for manifolds and so forth, so you can study. And what does it mean equivariant? Equivariant means there is a group action on X, and when I write G, I will be ambiguous in these lectures because in topology you want to use compact groups. But in algebraic geometry, you want to use reductive groups. And for every compact group, there's a complexification, which is reductive group, but it's slightly, I'll be a little bit ambiguous about what is the group. So this is a compact group. And so there could be another group action, H on Y, and a homomorphism from G to H, such that this map F is equivariant with respect to that. So what does it mean equivariant? If I act, so maybe phi, if I act by phi of G on F of X, that's the same as F if I act by G. And so cohomology is a functor from this data. So you want to go. What do you want? We want, right. And so this maps, I forgot to say, this maps you would like to consider up to some sort of notion of equivalence. So maybe up to, so in topology you would like to say up to homotopy. In other words, you declare homotopic maps to be the same map. And cohomology is supposed to be a functor, which associates to X, right, H of X. This could be, something like a complex of abelian groups, or modules over some ring, or many possibilities. And this functor is, so this complex, so maybe I'll say one, and this is supposed to be contravariant, so that means from H of Y, we should have a pullback map to H of X. And this complex itself need not be canonical because, well, what's the first example? The first example is maybe just simplicial cohomology. So, but it's it's canonical up to something called quasi-isomorphism. And so it's not. So let's just look at the example in a second. And so this is, and then this is the somehow the homotopic maps induce maps which are the same up to quasi-isomorphism. So it's this complex that's really the result. Usually people think about individual cohomology groups, but maybe better to think about the whole complex. And so what's the world's most basic example? So if I have ordinary cohomology, let's consider it non-equivariant. So let's consider I have some just simplicial complex. Then I can consider the complex, which is I'll write it as if it was the de Rham complex. So maybe delta goes to 1, so forth, which is this is like zero form. That is to say, functions on so this what? So this complex has simplices of dimension 0, 1, 2, and so forth. And so these are functions on zero-dimensional cells. This is similarly 1 cells. And I'm not specifying what are in which this, if you want to multiply functions, they may, if you want to add functions, they take values in some group. If you want to multiply functions, they take values in some ring. So maybe let me be ambiguous about that. 2 cells and so forth. And what's the differential? The differential is a discrete analog of de Rham differential. Namely, if I have a function, so maybe functions on oriented. So if I have an oriented edge that joins one vertex V1 to the vertex V2, then the delta of a function f evaluated on this edge, this is the value of f at V2 minus the value of f at V1. It's a gradient of the function. So similarly, if I have a cell, let's say it's a triangle, so then the value of my function on this cell, that's the circulation of a function on the edges, and I can compute its circulation value on this edge plus this edge plus this edge. Is that everybody familiar with that? And since the curl of the graph is 0, so this satisfies the property that delta square is 0. Now, of course, to the same topological space, I can associate many different complexes. Like, for instance, I can take this complex and subdivide it. Take one vertex, add one more vertex, and add a subdivision. And of course, the complex will be different, but the natural map, there's a natural map between the two, and this natural map is an isomorphism on cohomology. Right? So you identify, so this is a notion which is finer than isomorphism of cohomology groups, which is, but flexible enough. So you identify, you consider maps of complexes that induce isomorphism of cohomology as isomorphism. So this is called the derived category of complexes and so on. And so, okay, so this is that. Any questions about that? And so And what is the main, so what is the main property that this functor has to satisfy? So you would like to be able, so in the category of topological spaces, there's every map. So maybe I'll write a map X to F. Every map is the beginning of a long exact sequence, where there's something, some space called the cone of F, and so forth. And we'll discuss in a second. And the condition on this being a cohomology theory is that it should take cones of maps to cones of complexes. So I have a map, and I have a corresponding map on complexes, and I have a topological space which is the cone of that map. We'll talk about it in a second. It has to go to the cone of complexes. So what is this? So first, maybe the first remark is that every map between topological spaces you can replace up to homotopy by a very, very nice embedding. So people say, well, anyhow. So suppose I have a map. Let's call it, I have a map X, and this maps to some space Y, which I'll draw like that. So maybe have me some X is red, and it goes inside Y into something like a figure. So what do? I replace Y by something called the cylinder of this map. So maybe I'll just erase this part. So this is what is a cylinder? So I take a cylinder on X, and I glue it to Y along the map. Where's my yellow? That clear? So in other words, I add a cylinder on X which I attach to Y via this map. And it's clear that if I just contract every yellow line, if I contract it, that's homotopy equivalent. The cylinder, this is the cylinder of map F, and it's homotopy equivalent to Y. But the map of X to the cylinder is clearly under this homotopy equivalence. That becomes the original map. Any questions about that? So now, what does it mean to form a cone? Form a cone means, well, I just attach it quite literally. Let me try to draw it one more time. I can really attach a real actual cone on X. This really contracts. It really contracts X to a point. Right? This is the cone of the map. And now notice that there's a natural embedding. Y naturally embeds into the cone of the path. And so if I want to continue exact sequence, then I think I'll be reprimanded for continuing from this. Or maybe not. Maybe it's okay. So what's it going to be the continuation of this? Of the map. So previously I of every time. So what does it mean? Here I have an embedding of x into here, and here I contract x to a point. Now I have an embedding of y into here. Now the next step, I should contract y to a point. If I contract y to a point, what are we going to get? So if we take this whole thing, contract it to a point, we're going to get the suspension of x. So what's the suspension? The suspension is I take an interval cross x, and I identify all endpoints of an interval to one point. And it's a very nice exercise which I advise you to do. That the next map is, so if I have a map between spaces, there's induced map by suspension. So this would be a suspension of f going to the suspension of y. That's not obvious, but this is kind of the crucial point. And so this is how it starts. So this is, and then it's, starts circling. So this goes periodically. And so then if you'd like the corresponding map on cohomology, the corresponding map of complexes to be, so this would like this to be, it's like the, like if you've ever, right, sorry, if you don't, so okay, so maybe I should say it like this. If you don't know what is a cone of complex, you can, of course you can read Wikipedia, but you can also do, just imagine you have this kind of complex for x and for y, and you'd like to write the corresponding cell complex for this space. So the cells in that space will be indexed. So what the cells be indexed for? This kind of cells. So these cells, and maybe I'll draw them. That sort of cells are indexed by the cells in X, and the rest is indexed by cells in Y. Okay? But there's a shift in dimension because a k-dimensional cell in X becomes a k+1 dimensional cell in X. In Y, and so you have one complex, shift of another complex, and you use the attaching map to form a differential in the new complex. It's called the cone of complexes. And it uses this long exact sequence and so forth. All right. So for better development of the theory is it's actually better to work with, so this is a slightly technical point. If you've never heard about this before, you may ignore this point. But if you have, for a better development of the theory, it's convenient to have a base point. So in every space, choose a base point. And require that all maps take base point to base point. So if I have a base point in X, that map has to go to the base point in Y. And this has the implication that the base point, so then in this cylinder, right, so when I form the cylinder, there will be a whole line which goes to one base point to another base point. And this line, so it's a line. I can, up to homotopy, I just can contract it. So you take this line, you contract it, and that's called reduced cone. It doesn't change the homotopy type, it's just you want a base point you want to have a point, not a line, so you contract this. And similarly, when you do cone, you also similarly, you contract that. And here you contract this thing. So this contraction, this is called the reduced suspension, noted S. So that's a slightly better formulation for many purposes. Okay. And so now this has the fact that this is supposed to be take cones to cones has many consequences. Like for instance, So if I have the identity map from point to point, I can consider the identity map. I understand that people who want to study geometry, topology, and so forth, and study functions, and they generally speaking interested in non-trivial examples. But it's also good to start with the trivial examples and see what's it going to give you. So you can consider identity map from point to point. And if you plug it in here, you discuss that the cone of the identity map. Well, what's it going to be? It's going to be point itself, right? And so this says that this cohomology, this reduced cohomology, so this is important that I have this reduced cohomology. This reduced cohomology of a point, that's supposed to be a cone of an identity map. So a cone of the identity map has to be, in any reasonable definition, has to be the zero. Right? So if you somehow take, it's like Senya was talking about before the lecture. If I sum something and you subtract that something from itself, you have to better have zero. So that's good. Now then, if I also have a map. I have a map from X to yeah. What? Well, because this is the cone of the map is the point itself, right? So this has to be this has to have take cones to cones, right? So the point is a cone of the identity map between doesn't matter between what, it's cone of identity map between something and something. And so no, cone between two complex is a complex. Right? So there's a notion of maybe the axiom is cohomology of cone of F. This has to be the cone of the fullback of this kind of, maybe I'll write H of F. H of that's the axiom. So there's a notion of cone of complexes, there's a notion of cone of map, and so then you have to have that. And so since the point is a cone of an identity map, then it has to vanish. But you think, well, you think it's kind of bad, but then this is an aside remark, is that for every space, it's also kind of silly remark. So this is for any x. Yeah. Well, here it's cohomology. So you want a special. You want the. Oh yeah. Let's say you want the cohomology. Yeah. So cone of cohomology. It doesn't matter. It doesn't matter what stands here. It's the identity map. It doesn't matter what stands here. So this cone of identity map may better be zero. So for any space X, we can consider the space X plus, or X. I don't know. Do you prefer plus upstairs or downstairs, or people have various conventions? Well, let's say downstairs. X plus, which is a silly construction, which is X disjoint union of point, where you declare this new point to be your marked point. So this is then the cohomology, kind of like the cohomology of X plus. This is kind of the old cohomology, old unreduced cohomology. When you don't like reduced cohomology, you can always add a point and have it as a marked point. It's not, I'm not saying anything particularly profound. Does that make sense? this is this is nice because if you look at a sphere, the sphere of any dimension other than zero-dimensional sphere is connected, with this if you consider modular point, the cohomology of, in other words, the cohomology of zero-dimensional sphere, that's like the old cohomology of a point. So zero-dimensional sphere, that becomes your kind of the new point. There's some uniformity. Right. So what I was going to say. So now we have a map from X. We can consider map embedding of X into cone over X. And then you get. So if I embed X into cone over X, so imagine there's no Y. Then the next term, that is this. This would be this is the suspension of X. And then you get the cone of the suspension. So here's suspension of the cone. Okay. But the cone over X, that's contractible to a point. So this is a point. And so its cohomology is 0. That says the map, that says that the cohomology, did I miss something? Yeah. Goes to suspension of. Right. So this is, you get, anyhow, so this is, maybe it's not necessary, so it goes somewhere. That says the cohomology, so this is a point, so this says the cohomology of this is the cone, well, with some shift, shift of the cone of the zero map, of the map 0 goes to cohomology of X. So the induced pullback map is 0. So it just says that cohomology of that is the shift. So this is cohomology, the ith cohomology of the suspension of X. That is the I minus first cohomology of X. Which is super important, which says that if we, since suspension changes cohomology only by shift, this means in the sequence, so at some point we're going to get, this sequence goes forever, so we got some point n-fold suspension of X, going to n-fold suspension of Y, and so forth. And by this principle, it's enough to look somehow at what happens for n much bigger than 0, because you can, whatever computations you do here, you just then shift your complexes back. That makes sense? But these spaces have an extra structure, because if I study maps, space of maps from suspensions of X to anything whatsoever, maybe call it Z. This is for any Z. This is a group. How is it a group? Because if you have a suspension of X. What you can do is you can pinch it one more time. So this maps to kind of two suspensions of X joined at a point. Okay. And so if I have a map here, a map there, I can compose it with this map, and it's like the definition. It's just like the definition of a product in fundamental group. So if I have a map here, map there, I can compose it with this. And moreover, so this works for any n. So for map for n bigger or equal to 1, this is a group. And in fact, for n bigger than 1, this group is abelian. It's the same proof. Same proof as for pi2 of z. So here, this maps here, I can add. This is the maps I can add to one another by this rule. And it's to see that this operation has to be the additions of maps in this sense have to go to the addition of maps in the sense that you have some category of complexes between the maps between them you can add, and that has to go to the same. I mean, how do you prove? You have some map, so you have some map between two abelian groups, which is from a product of two abelian groups to another, which is a homomorphism, and equals to the identity map if you restrict it to one group cross 0 and 0 cross the other group. Then it has to be the addition. Right? So this is a functor which is not just a functor on topological spaces. You have a notion of addition of maps, and that preserves that. Okay. All right. So now I guess we need an example, and our first example would be. So maybe let me look at my notes briefly. Right. So I think we're good. So for today, our main example of an equivariant homology theory like that is so somehow today's example is equivariant K theory. So what is it? So if I have people who know me long enough, they make jokes how I always, when I need to draw a vector bundle, I always draw something like that. But okay. So this is so let's have some space X, and X is just let's say compact Hausdorff space or something like that. And so then we discuss the notion of a vector bundle over X. And now, what does it mean that the bundle is equivariant for the action of some group? Means if I have some point x, which my group takes to a point g of x, g, then the group action lifts to the total space of the bundle. So I have some map between the fibers. So maybe fiber at the point x and the fiber at the point g of x. So there is a map between them, and this is a linear. Okay. So think about it as sort of, we study representation of a group as an action of a group on a vector space. And now it acts on a bunch of vector spaces. We're permuting computes the index, which acts, and on the vector space itself acts linearly. For instance, k g of a point. This is what? This is, so you have a vector bundle over a point. That is to say, representation over group G. So this is representation. First to say, maybe some semi-ring, in which representations have a notion of direct sum and tensor product, as do general bundles, and then you kind of add subtraction like we did yesterday, and this result is called representation curve. Representation. Ring of G. And concretely, what this ring looks like, well, it's if we have, so maybe inside T, here I have a maximal torus. And the ring looks, again, maybe this. And the ring looks maybe with coordinates Z1, Z rank, and the ring looks something like all Laurent polynomials in ZR, which are invariant under the Weyl group. You have to, worry a little bit about simply connected, non-simply connected. Let's just not worry about it right now. So for GLN, these are just symmetrical Laurent polynomials. So because the representation is determined by its character, the character is some Laurent polynomial, and the basic theorem of representation theory is that if I allow also subtraction of Laurent polynomial, I get all Laurent polynomials integer coefficients. Okay, and then so this means, so this is equivalent. So this kg of x. This is, well, maybe we'll start with k0. Sorry, k0. So since we're doing homology theory, so kg of x is again, this is representative that is equivalent vector bundles with operations addition, tensor product, and you add formal subtraction. And this is a ring, and also a ring with a homomorphism. So with a homomorphism from, so this is a ring. And there's a homomorphism from this K naught G of 1. What? Weyl group, yeah. And maybe I'll, depends whether your group simply, I don't know. You have to say what these coordinates are. So, all right. So this is what does the homomorphism means concretely. So in one sense, of course, it corresponds to there's an equivalent map from X mapping to a point. But concretely, this means if I have a vector bundle, I can tensor it with a trivial vector bundle, which has a non-trivial group action. So that's this homomorphism. And so now, in So now if we use this formula, so now we're supposed to have this formula. So this formula will say that minus 1, k minus 1 of gx, that is, we can just define, because we would like that formula to be true, we define it to be the k through k naught g of the suspension, where on this, so when you suspend, there's some interval, and here the group acts trivially. Here. In principle, there's operation of suspending by a non-trivial representation, but we're not, this we can study this later. There's also operations like that. So if you have a kind of a, you have a representation, you can form the corresponding sphere by adding a point at infinity, and that will have a suspension by non-trivial representation of a group. We'll just do that for now. And then, so this lets you define at infinity. Yeah. You also always at infinity. Yeah. So this lets you define these functors for all negative. Yeah. It doesn't act on this part. So that when you form the suspension, what's the suspension? You take your space cross an interval. So in other words, in suspension, there is this direction. And group only acts on it, doesn't have a separate action along this direction. In principle, it could have, if I have a action on one direction. So a compact group can have only, on a compact group, the only thing you can do is if it has you can flip the orientation. But it's, okay, that maybe, we're not going to consider that now. But so on the suspension, in other words, on the suspension, it acts just by acting on x. It doesn't have a separate action on this coordinate. Is that very clear? Yeah, but base point is all. Yeah. Yeah, the group action, right, has to be fixed. Right, so base point is fixed. So right. So it's an excellent point. So the base point fixed by the group. And usually you achieve this by so usually you achieve it by saying I will have just another separate fixed point like we did over there. And then so that in that sense it's better. So in this sense, if you want a homology theory, you have to have 0 for a point. And so then it has to be, maybe I'll write it like this. So usually, so people, when you have a base point, people have this k tilde, which just means you have a bundle which is trivial at the just zero bundle at the fixed point. Zero vector space. Restricted to the fixed point, it has to be a zero thing. Zero representation. No. The base point, so there's the point discussion, the base point of the current situation, you want the base point to be fixed. No, it's just a point. It's a point on X that has to be fixed by the group. And usually you achieve it by just adding a separate point. I mean, it's like we had this discussion over there. You can reduce everything to the situation by just a separate point, which is fixed by the group. No, of course, that's no need to be connected. So in other words, I introduced this extra fixed point here. And the condition is that at this fixed point, so maybe I'll write it. So this is this ring that was before. This is the same. Sorry. This, like if you've never seen this before, then maybe this is a little annoying. But this is the same as k twiddle of G0 of X union disjoint base point. And twiddle means that if I have this virtual vector bundle, you restrict to this 6 points, you get nothing. Just really 0. What? It's equivalent. It's somehow just for if I want this, if I want all this. So if you want this kind of, if you want this rule to hold without exception, it's better to have fixed point. Otherwise, you run into this issue with the zero-dimensional sphere being disconnected. So that's so. That's a right. That's the reduced suspension. Thank you. So maybe I'll put the twiddles here. Means I have base points everywhere. So again, yeah, right. There's a sequence. It's just at every point. All the things that's colored in blue in this picture. You just subtract them all to a point. That's your reduced sequence. It's homotopy equivalent to the original sequence. So this, right, going back here, this lets you define K groups for all negative indices. But then comes kind of a landmark result in the field, and we'll talk about it later. This is the Bott periodicity. That says that K0 of two-fold suspension is in fact equivalent to the K0 of your original X. And so this lets you, by this rule, you define Ki to periodically for all I. This is an important result. We'll talk about it. We'll talk about it later. Complex vector bundle, right? Everything's complex, and this is a generalization, more general result, and we'll talk about it now. It's called Thom isomorphism. And so, what does Thom isomorphism say? This is a very important notion. Suppose I have some space X. Again, X can be anything. But over X, I have a complex vector bundle. Right? And contrary to what I did here, I draw it slightly differently. So maybe I'll have. I draw it like this. So if I have a V is a complex vector bundle. Then associated to this complex vector bundle, I can have a Thom space of that vector bundle. What is that? I take, well, maybe some infinity in this vector bundle, which is equivalently I can take a ball of some fixed, introduce symmetric, have a ball of some fixed radius in every one of these vector bundles. Or I should have done it in blue, so because we collapsed the blue things to a point. And all of that, all these infinities, all of them I collapse to a point. So you can imagine you can imagine this as an infinity in vector bundle, or you can imagine you introduce some metric, have a ball of some radius, and then you take a sphere, and then you collapse all the spheres to a point. Okay. So and Thom isomorphism says, so this is Thom isomorphism says that the K theory, like K twiddle G, and the bundle can be, can be equivariant vector bundle. K twiddle of this Thom space of this vector bundle, that's isomorphic to K twiddle G of your origin length. For instance, if you take a trivial, so for if V is a trivial bundle with fiber C, then you get that twofold suspension. This is this Bott periodicity. Yeah. Yeah. And so maybe while we're at this point, I want to point out, then this is, it's isomorphic and also not isomorphic, kind of yes and no. Because, yeah. Fine, yeah, torus is fine, yeah, torus is fine. I think, no, not semi-simple. Compact. You can take torus. The torus is interesting. Yeah. It doesn't have to be semi-simple. No semi-simple. No. Why semi-simple? Compact is enough. Right. So this is the because this isomorphism is, so how am I supposed to say it? So this is, this side is really so this side is really so what Thom isomorphism says that there is some particular element here, which is and we'll talk about it in a second. That so how are you supposed to in general somehow think about it? So maybe I'll explain this. So so if I take so if I have, how am I supposed to in general I think of elements in K where I collapse some subset A, maybe some subset 1. If I have x and y, or y and x, how am I supposed to think about K theory of x where I collapse y? One way to think about it is you can realize the elements concretely here. You can realize by complexes of vector bundle on X that become exact when restricted to Y. So this is, maybe more naively, of course, you can think of this as complexes. Maybe have a one vector bundle and another vector bundle and a map between them that becomes an isomorphism when restricted to Y. But it's more flexible to think about complexes. So that you have a complex of vector bundles and amounts to nothing when I restrict to Y, but otherwise it has some non-trivial cohomology. And so if I think about these objects concretely, that these are complexes of vector bundles on the total space of V that are exact away from the zero section, X, the zero section. That makes sense? So I wanna, in principle, collapsing Y means I have an element in this group is some two elements in K theory of X that become the same when I restrict to Y. I can package this property into I have a complex of vector bundles of X that becomes exact when I restrict to Y. And so here it means I have complexes of vector bundles which are exact when I go away from the origin, away from the zero section. But right, some.
What do you mean when you say that the complexes?
So okay, maybe one more time. I mean, infinity is homotopy equivalent to the complement of the zero section. So in general, what's an element in the K group is in principle some kind of difference of vector bundles. Right? And so then an element in here is such expression in X where when I restrict to Y, I can these two things really cancel. Right? It becomes really isomorphic vector bundles. And I can phrase this property in the sense that I have, instead of thinking about like this, so have some kind of isomorphism by the Y, this I can phrase by having some, like for instance, I have some map that is isomorphism away from the subspace. Which is isomorphism on Y. A more flexible notion is to have some complex. So this is an example of a two-term complex. A more flexible notion, so this is the fact that this is isomorphism is a statement that this complex is exact. A more flexible notion, I have a longer complexes, so about complex, and then when I restrict it to Y, that has to be exact. And here I have, so by that description, if I need a complex of vector bundles on the total space of V, such that if I look in the complement of the zero section, that becomes exact. All right? And so this object here, this is this is a module over K of X. Because if I have some complex, I can tensor it with anything I pull back from X, from the base. And if it was exact somewhere, if I tensor it with something, it still remains exact. And Thom periodicity really says that this module and so Thom isomorphism says this module is free, rank 1, and the generator is something very, very specific. It's called the Cazul complex. Of the zero section. And we will talk about this. Well, maybe still we'll probably maybe still talk about it today. There's some very, very explicit complex on the total space of V, which is in fact generator of this group. But it's not, this is being a free module of rank 1 and being isomorphic to the ring. That's not exactly the same notion. And what we'll see then in elliptic cohomology, this will correspond to some scheme, and this will correspond to a line bundle on that scheme. So kind of rank 1 locally free object, but it's not a trivial object. This is why in elliptic cohomology, when we get to elliptic functions, in elliptic cohomology, Thom isomorphism is strictly speaking false. But that's the beauty of elliptic cohomology. Yes, please. So it has to be, when you mod out by Y, it has to be exact on Y. So maybe I misspoke. So exact away from the zero section. So this is my Y here, that's my Y. This is Y, which is also homotopy equivalent, just the complement of the zero section. If I have a sphere, I take all the complement of the zero inside a ball to the sphere. You have a complex, so you have a complex of vector bundles. And that complex, when I restrict it to complement of the zero section, that becomes exact. Okay. Right. So, and we will, maybe let me look at my notes and see, maybe it's actually can pass straight on to the discussion of this Cazul complex. Right. Maybe so from at this juncture, so maybe I'll put a pointer for the future. So eventually, this Thom isomorphism this is what is used. So eventually I tried to say at the end of previous lecture that all cohomology theories, they're all more or less the same once you do functorial maps. Once you just pull back stuff under maps, it's very difficult to tell the difference between different cohomology theories. The real flavor of cohomology theory manifests itself when you try to do push forwards. So that's when you try to go against the grain, then you really see the difference between K-theory, between cohomology, between elliptic cohomology. And it's the Thom isomorphism that lets you, that's the key to defining, so really defines. This is how you define the push forward. In K-theory. And because it defines for you the baby case of the push forward, namely the push forward from the zero section to the ambient space. So you have a map K of X. This is the Thom isomorphism. Goes to the K theory of the Thom space. But the K theory of the Thom space are this something, the some objects on the total space of the vector bundle that satisfy some condition. They just sit inside. They naturally map to the K theory of the total space. So this map is functorial. This is just functorial map, and this is Thom isomorphism. So you get to push forward something because of the Thom isomorphism. Right.
Total space of what?
Total space of the bundle V. What? No, it's not. That's not a functorial map. If it were a functorial map, that would be also the Thom isomorphism would be also true in elliptic cohomology, for instance. Yeah, so this is. Yeah, it is. It's class. If you think about it as it's going to define you a line bundle on some schema. That line bundle is not trivial, because this will correspond to like a theta function. So maybe so maybe Alani, I'll write one word and then you'll see. So if if my group is U, so if my group is maybe S1, so U1, something, right? So then elliptic G-equivalent cohomology of a point, as we will see. So we think of this as there's no ring, but there is a spectrum of that ring. So there's some scheme. So that's the elliptic curve itself. This is the elliptic curve itself. And over that point, I have a bundle which is just the defining representation. So C, and here I have the defining representation. Right. And so then the Thom space. So then Thom's somehow what Thom space of that representation, of kind of embedding of zero into defining representation, that corresponds to the line bundle, which is, so you have your elliptic curve has the origin, maybe call the origin 0. And this corresponds to the structure sheaf of the elliptic curve, which is twisted down by 0. So functions that vanish at 0. So this has a section, also this kind of sort of has a section like 1 over theta of x. Oh, sorry, theta of x. What? Yeah, everything would be over elliptic cohomology of a point, and so this is 1 over the theta function. That's kind of like this bundle doesn't have a section, but it has a meromorphic section, which is that. Yeah, anyhow, this is just an example. So this is now with some time. Let's discuss a very, very special case of the stomach. Well, maybe related, kind of special and general case. That's a very, very instructive computation. Maybe we won't be able to do it completely today, but let's start. So if I have a vector space, maybe call it V. So somehow isomorphic to Cn. And on this, I have the defining action of GLN. Or GLV. And so I can ask, what is, so this is my group, maybe I'll write G. What is the G-equivalent K-theory of the projective space? Okay. So this is something we were going to compute, and we will, by computing it, familiarize ourselves with the Koszul complex. So what is projective space? Projective space, this is, no one insult your intelligence, but it's the quotient. You take out the origin, and you mod out by GL1. Now, this quotient is a free quotient. If I have a bundle on a free quotient, it's the same thing. So this is very important. So maybe I'll write it here. So I apologize for. So if I have, so kind of really important general property of K theory. So if some group G acts on some space X freely, then KGX, that's just the same as KX, the quotient by G. Because what does it mean to have what does it mean to have a bundle, G-equivalent bundle in a free orbit? You just take any vector space and you just move it around. So this, by this reasoning, is KG cross GL1 equivalent K theory of V minus the origin. What? Here? This is the quotient. So if I have a no, but there's no more action here. You just take the quotient. Free action. If you have the free action, you just divide. So this is this complement, which is the which is what? What? Yes, you can generalize the statement. That's true. So right. So let's go back here. So this extra GL1 is just the center. So if you have a center of the group, you can have a separate copy of the center that acts with the group somehow. No problem, right? This is the center. So you kind of enlarge the center, the very center of GL1. Okay, X kind of twice, GL1. X kind of twice here. Right? But so now, what is it? What's an element in here? An element in here is, well, we have a map from K G cross GL1 here of the whole space. We can restrict it to K GL1 of what we want, and this is, here is the Thom space. G cross GL1, covariant of the Thom space of the embedding of 0 inside. No, I'm just by definition. So this is these are so for in this picture here, what we were collapsing before. This is kind of like in that picture. That is why. This is what we want to collapse. Right? So what does it mean? So there's a map here, and you can convince yourself this map is surjective. And this is the Thom space. So this part is easy. This is just the same point, right? So this becomes what? So when I write Thom spaces, I like to denote the base and the bundle. Remember both the space and the bundle. Otherwise, sometimes you get confused. What Thom space or what? So this is just my kind of mnemonic thing, that what is the base and what was the bundle. Base is just the point. Yeah. No, not suspension. Just really, it's a vector space. So it's a bundle over a point. So bundle effect over the origin. Right? So this thing is point. So this K theory is just, so this is what we decided. This is K theory of a point. So we can write it Kg of a point, a joint polynomial, one more variable, maybe call it U. For this center, which is So the base here is just a point. This example. Base is a point, and I contract the complement. I contract the complement of the zero section. So it's a sphere, yeah. Yeah, it's a sphere. So okay. So what is the? No. Yeah. So okay. So you take. So let's just continue. So I just copy. So G cross G1 of this Thom space. This is what? These are complexes we just discussed. Complexes of vector bundles exact away from the origin. 0. And these are the groups as GL cross GL1 equivalent. And this equivalent, this GL1 equivalence means the maps are homogeneous. With respect to, so what does GL1 act? It acts by just rescaling. So if I have a maps which are supposed to be equivalent, that has to be composed of polynomial certain homogeneity. And so homogeneous implies all the maps are polynomial. Right? If I have a, so I can think of the same category in the category, so the same kind of object. So instead of thinking of complexes of vector bundles, I can think of the same thing as complexes. Can replay all these complexes. Think of all these complexes as, well, I shouldn't write in red. As I should, or rather, I should have written this in white, and what I about to write in red is graded as complexes as graded recurrent complexes of, well, let's choose some coordinate rings, and maybe call it, x1 through xn. These are the coordinates. Or functions in my D. So there's a notion of a vector bundle in algebraic geometry. It's a module over ring of functions on the algebraic variety, which is locally free. So instead of module over all possible functions, I can view it as module over polynomials. So in algebraic situation, I have a very much more flexible notion. I can embed it. So no, there's a GLN action here, and that has to be, so these are coordinates in my space. And GLN acts here. Whatever I'm going to write has to be equivalent with respect to that action. Make sense? So, complexes of modules, right? Of modules. Modules, right? But in algebraic geometry, there's really no need to restrict yourself to modules that are locally free. You can consider any finitely generated modules you can take. Modules, i.e., known as coherent shapes. So what's an example? What's the module that we want? We want to take the module, the structure, what's it called? Particular module we want is IE. You can take what's called the structure shape of the origin. That is to say, you take your ring and you mod out by the ideal M, which is the ideal generated by all x's. This is how polynomials act on functions, on kind of delta function at the origin. Every x kills it, and the constants will multiply. Does that make sense? It's kind of the maximal ideal of the origin, if you'd like. So you take an ideal generated by all coordinates, you mod it out by this ideal, so this is isomorphic. As a module, this is isomorphic to just C, with generated or delta function at the origin. And this is how my guys act. And this is obviously an element so this is, and in algebraic geometry, it's very, if you look at this coherent shape, it's very easy to see that this is the generator of, so if I take in algebraic geometry, I take K-theory of coherent shapes of V. I have, again, a map K-theory of coherent shapes of V minus the origin, and this will be surjective. And And here is the K-theory of coherent shifts. With just support, so this is just kind of support at the origin, which is just generated by K coherent or point, all right, so G across whatever of a point times this kind of times the structure shift at the origin. In algebraic geometry, it's essentially obvious that if you ask for coherent shifts which are 0 outside of the origin, they're all multiples of this. Well, because, I mean, axis, what does it mean it has 0 outside of the origin? It means the coordinates x have to act nilpotently. But if the coordinates x have to act nilpotently, that my shift gets a filtration by terms which are isomorphic to this one. So it's in our one word. What does it mean? What does it mean to look outside of the origin? It means some of the coordinates has to be non-zero. Some of the coordinates has to be invertible. And that means that coordinate has to act nilpotently. Because if you invert that coordinate, then you get 0. So that has to act nilpotently. If I act something acts nilpotently, then it gets a flag. So you get a filtration of things in which it acts just by 0. So you get the condition that this is just the only thing. What? Why it's exact here? Oh, in general, it's not. No, I mean in this situation, it in fact will be, but in general, it's not really exactly. So oh, here it's because every coherent shift you can always extend. You pick some presentation, you can always extend it. But in general, there's a connecting map from K1, and this is right. So what we need to do somehow to go back to the world of vector bundles, what we need is maybe I'll draw one picture and this will stop. So what we need, so what's the Kazul resolution? Kazul complex, that's a minimal, it's a resolution. In fact, minimal resolution, a resolution of this module by a free module. So this says in the world of algebraic geometry, this guy generates what we want, and to bring it back to the world of vector bundles, we need to represent this guy by vector bundles. We need to resolve it by vector bundles. And how does this work? So I'll draw a picture, and maybe this is where we start next time. Well, imagine I have two variables. So let's say for concreteness, I have two variables, x1 and x2. Then I have a module in which, so maybe this is a picture I always have to draw. It's very nice to have a table of all possible monomials. This can take much longer than 2 minutes I have to the end of the lecture. So you can put 1 here, x1, x1 square, x1, x2, x2, x2 square, and so forth. So my module is this. So I have an ideal, which is this. The red in the red. This is a picture of the ideal. These are all. So if I look at the ideal generated by x1 and x2, then well, this is the picture of that ideal. And the picture of the quotient by this ideal, this is my function y, which is the generator of that C. Now, if I want, so if I start drawing my resolution, so I have my O structure sheet of the origin. By definition, it gets the surjection from the free module. Maybe I call it, let's denote this ring R. So it gets a map R, and the kernel of that map is generated by this ideal. Right? So this ideal has two generators, x1 and x2. So this means the kernel of this map is x1 times R plus x2 times R. That will generate the kernel of this map. This means if I take these two summons, maybe this would be the yellow, and this would be the, what other colors do I have? Maybe have it blue. Then one would be, one will generate these monomials, and the other will generate these monomials. Now from this you see that you're subtracting everything generated by x1, x2 twice. So the kernel of that map would be x1, x2 times R, and that would be the resolution. So this is, if I have some other colors, let me see. No, there's no other colors, so maybe we'll start with the red again. So this would be, if I now do this guy here, that this is this guy. So this is this generator is this generator, and that the red generator. And you can imagine that if I had, so this is a complex which has, maybe this whole complex rather. If I take, so if I have you can imagine if I had n variables, that will be very similar, except I'm going kind of, the terms in this complex corresponds. So the terms in this complex corresponds to points in this case it's 2 by 2 squared, and then in n variables it's 2 to the, so it will be, the terms will correspond to, the terms in this complex will correspond to n times. The points in the 2 by 2 by 2 by 2 box. And that's called the Kazul complex, and we will, and I'm over time now, we will write it as a, to finish this computation, we will need to write this complex as a module, as a complex of GLN equivalent modules, and see what it says. Okay, that will be no lecture tomorrow, so this will happen on. You have to. You can figure it out, I'm sure, but also good to keep the suspense. Yeah. All right. What? Complex means complex means, what does mean complex? Means they have some vector bundles and map between them such that the composition of any two successive map is 0. Something like a cell complex, yeah. So this is like the composition of this map is 0, because this generates the kernel of this map. So in fact, this is resolution. It's in fact exact. At every step, the image of the previous thing generates the kernel of the next.
Okay, let's first thank Andrei. Any questions?
Can you go to this other blackboard?
Mm-hmm.
Yeah.
Which
so
one?
this K of total space of T,
Uh-huh.
isn't that the same as K of X?
Um, uh, um, right. So this is you should think of it like this. So this is right. I mean that's a good point. This is the in this case it is the same, but you should imagine that you can have a situation. So this is a good point. Maybe I'll explain. So suppose you have some space Y, and then you have an embedding of X such that the normal bundle, so some embedding on X, and there's a normal bundle Y to X, and you want this to be complex. Then there is a functorial map from the from K theory. So there's Y, since Y Tom space you get by some kind of collapse. So there is a map from Y to the Tom space of the normal bundle. And so there is a map, therefore there is a map from K theory of the Tom space to K theory of Y. Right? And so then if you use the Tom isomorphism, the K theory of X, there's a Tom isomorphism. This defines you a push-forward map.
Other questions? This one. This one. So in principle, so right, I mean, so in principle, I keep talking about K0, but the point is that, of course, in principle, that will go to K minus 1. But since the projective space has cells of all even dimension, it's easy to see that K odd of projective space is 0. You have any, so this is in general. Suppose you have a space of which all cells are even dimensional. Then K odd of that space is 0. So this is just like a cone, like we before had. This is embedded in here, and we collapse it to get the Tom space, right? So we get this is a cone of a map, and so this means you on K groups it will induce a long exact sequence. So this would go to K. This will go to K negative 1. But K odd over any space which has only even cells, that's 0. Okay, I suggest we thank Andrei again, and other questions will go to discussion session.
Извини, что я так
Да
формулирую.
не,
но
ну,
мне
спасибо, я стараюсь.
Вопросы лучше не. Включил, да. Все.
Okay, so it's time for us to continue. And we now have the second lecture by Nikita Nekrasov.
So yesterday we were talking about simple classical things. Today we'll go to more complex things. And then the day after tomorrow we'll start quantizing and dualizing and do other things. So today we'll complexify. So complexification is it's a process, it's an art, it's a mindset. So R becomes C. Z2 becomes, well, depending on how complex you are, could be U1, could be C star. And so classical So what happens to classical mechanics? Here we have options because yesterday, remember, at some point we were discussing that we're discussing paths, spaces of paths in phase space, and we would like to complexify the space of paths in phase space, and so one way to do it is to complexify the phase space, but keep the paths real. So if I denote my phase space by P, I'll make them into paths in the complexification of the phase space. And so what's the complexification of phase space? That's complex manifold with holomorphic symplectic structure. So this is so it's a 2-0 form, which is closed and non-degenerate. So why do that? There's various reasons to at least think about it. One is to make use of complex analysis. So even if your original problem is very real, involves dynamics in real phase space, you might want to do statistical mechanics when you integrate over the phase space some measure. Probability measure may be induced from Liouville form, Liouville measure, and the Hamiltonian. But you're interested in integral quantities, in averages. Now, to compute an integral, you don't have to integrate over the space you are given. You can use Stokes' theorem and deform your integration contour. And so then, more often than not, you end up integrating over contours in the complexification of original space. Yes, Conor? You see, that's good. Yes, that's the thing. So real paths, real paths. Real paths. So because what is time? Time is a way of, okay, I'm not going to talk about what is time, but time is just a label. Time is just a label. And so I label points in my phase space. Now I want to make this space of this path a complex space. It just means that I make my target complex. It's a literal complexification of the space of paths. Now, there is another approach. So this is a bifurcation. Take complex paths in the original space. This is where string theory starts. So you replace word lines by word sheets, and that gives you another way of kind of complexifying the problem. We will find eventually, maybe if time permits, that these things are actually related. That if you really try to, when you really start approaching, especially the approaching quantization as a study of periods, you will end up studying not just paths, but maps of high-dimensional objects into the phase space. But we'll get there in due time. So now that this simple process kind of allows to freely talk about things which otherwise are hard to discuss in full generality. And that is, so let me continue now with my example of the many-body system. Which I want now take to be elliptic. So I will write the Hamiltonian as I did yesterday. Again, maybe with the same mistake I did yesterday. But now I will generalize the potential, which was the rational or trigonometric function with the second order pole at the diagonal, to an elliptic function. So this is Weierstrass a function on some elliptic curve, which so it's a function which has two-dimensional lattice of periods, and the parameter which characterizes this lattice tau is a complex number with a positive imaginary part, and unless you make tau very special, like purely imaginary, this function is not real on the real axis. And so it would make the dynamics formally defined by this Hamiltonian look awkward unless you allow P and X to be complex valued. So I mean, just thinking about this problem makes it natural to allow I mean, I wish I knew. Okay. So it is natural to allow P and X to be complex. Okay, maybe I should be careful. But then an interesting phenomenon happens. Now it turns out that the fact which on real axis, so when P and X were real, and you studied the configurations of finite energy, and so it was obvious that for the real function, you cannot let points collide because that would require infinite energy. Once P and X become complex, you can actually keep the energy finite by allowing particles to approach each other by making the momenta very large and complex in such a way that the potential compensates the kinetic energy. So the phase space is actually more interesting, and so it's we can take the cotangent bundle to this elliptic curve to the power n. I will not delete diagonals. I will divide by the symmetric group, and then I will resolve the singularities of this symmetric product. So it is actually a smooth hyperkähler manifold. Hyperkähler in this context means that I mean I did not introduce enough data to really appreciate what it is. It means that in addition to the symplectic form, which is in these coordinates, which are not the global coordinates, it's just dp dx, it also has a metric. Say it again. Sorry, what is n is I want to n. Yeah, well, if n is equal to 1, then you just take T star of E. If n is equal to 1, there is no potential. It's just one part. So n equals to 1 is also true, but it's kind of trivial. So your phase space is just T star of E. And the Hamiltonian is just 1/2 P squared. Okay? Yes? No, it's a parameter. So tau is a parameter. Just like nu. So nu is a coupling constant. It's a parameter, and tau is also a parameter. Just the model has some parameter. So there are different physical contexts in which this arises. You can say that your particles still live on the real axis, on a circle. So there is a, okay, now I can get to use the color chalk. So inside this elliptic curve, there is an actual real S1. And of course, classically, if I put initial, okay, so this is now. So if I start with the configuration of points which are real, which all belong to this circle, and put some initial conditions for momenta, let's say also real, then for tau complex, the Hamiltonian will will force these particles to move around, so they will not be confined to the circle. But you can still restrict your motion by forcing, by somehow adjusting momenta so that the coordinates continue to be real. And so you can, so when you quantize, you can look for, so if we write so in quantum problem, we would make out of this function a differential operator. So the operator will be acting on functions, some kind of functions of x. And even though the functions will have some, they're analytic, so they're defined on in some neighborhood of this circle, you can restrict your functions by requiring that they're normalizable only when x is on the circle. Nevertheless, you don't have to restrict tau to be purely imaginary, so that the Hamiltonian will have in general, so this operator H2 hat, which is H2. Will have in general complex eigenvalues. As functions of nu and tau. So you can make both parameters nu and tau complex. So what is not quite trivial and interesting is that on this true phase space, the symplectic form omega, despite this formula, despite the appearance that it looks like an exact form, is actually not exact. So these coordinates p and x are not the global coordinates. They don't cover everything. And so this form has a non-trivial cohomology class. Is non no, it's not. No, it's not exact. It's not exact. It's not exact. It's non-trivial in cohomology, and so there is a two-dimensional, real two-dimensional sphere inside the space, such that the period of this form is proportional to nu. And so the coupling constant, the coefficient in front of the potential term, actually measures the topological non-triviality of the symplectic form. So there is a stool which arises because of this resolution of singularities. Maybe we can discuss the case n equals to 2 to see how it comes around, how it comes about. So let's take n equals to 2 case. So we'll, and let me, for simplicity, just restrict to the so-called center of mass. Frame. So it just means that we, in the language of yesterday, we perform the symplectic quotient. So this phase space is acted by the group. The group is actually the elliptic curve itself. So this group acts by shifting all coordinates by the same amount. So this transformation doesn't change the Hamiltonian, and the moment map for this the momentum map in this case is precisely the momentum. It's just the sum of the sum of all coordinates. So we can, as an exercise, we can perform the reduction by fixing the momentum to be 0 and identifying configurations of points related by the overall shift. Yes. Yes.
The left side is seems to be purely geometrical. How it knows about this.
That's why we're going through this example. Yes. This is, it's, you see, the point is that, okay, we will go through example, but I just want to repeat what I said. What I said was that the coordinates P and X don't cover the whole phase space. You add something to the phase space while keeping the fact that the Hamiltonian is well defined. So you can allow X1 approach X2 at the same time P goes to infinity in some way, yet the Hamiltonian is fine. Yes, nu is determined uniquely. Yes. What do you mean? What do you mean uniquely? Nu is I just wrote nu. I mean,
How does this?
oh, nu goes to minus nu. I mean that's the question.
I mean, this integral. How does it knows about Hamiltonian?
Okay. The way I resolve the singularities of this symmetric product produces a manifold which has a complex structure which depends on nu. So okay, so the phase space, this reduced phase space, the reduced phase space in this case is the quotient of the cotangent bound to elliptic curve. Elliptic curve here is just being, let's say, x1. So it's x1 minus x2. This is the coordinate on this elliptic curve. This is the invariant under these transformations, and z2 exchanges x1 and x2, and so it maps x to minus x, but it also acts on the momenta. So because it exchanges momentum p1 and p2, so let's say, so this is how my group acts. So so there is a naive phase space which is just a quotient of the cotangent bundle to the elliptic curve by the involution which changes the sign. So that involution has fixed points. And now each fixed point locally, first of all, do we know how many fixed points does it have? Because I said so. Okay. Let me erase that. Oh, I'm supposed to go from left to right. Four. Good. Very good. Indeed, it has 4 fixed points. So, okay, so this is my picture. So the elliptic curve has 4 points on which the involution x to minus x, which are fixed under this involution. So these are the points x equals to 0, 1/2, tau over 2, and 1 plus tau over 2. And then we have a fiber of the cotangent bundle. And so so in this fiber, the involution also acts by changing sign. So the 0 in the fiber times this point are the fixed points. So let me look at the at this fixed point, and then it will be easier to will be analogous at other fixed points. 4. P. So P goes to minus P minus X. So we have, so X is defined up to the shifts by integers and integer multiples of tau, but P is defined as it is. So the only way to be fixed is to set P equals to 0. Yes. You heard what? Sorry. So the right, but okay. As Senya would say, this is not a question. So. Yeah, it's more subtle than that. Of course, 16 is a number of fixed points of the involution acting on the 4-dimensional torus. So if you try to make elliptic both coordinates and momenta, this whole phase space now is built out of the abelian varieties of dimension 2. And so then it's then 16 is important because that's how you make K3. So then, so what I'm presenting to you is the baby version of K3 manifold. But the special feature of this story is that the local geometry near each of these fixed points is identical. In general, if you just in general, this space has more complex deformations than are available to us. You can so at each of these fixed points. So this is the local picture. I will explain why I draw them this way. So you can resolve singularities by gluing in a two-dimensional sphere at each of these points. And in general, you can make the spheres be completely independent of each other. So you would have 4-dimensional space of parameters, but this will not be related to the integrable system which we're discussing. So for K3, for example, each of these 16 fixed points on the 4-dimensional torus comes with its own parameter, and that's why K3 eventually has lots of complex deformations. In our case, we have more symmetry, and so we have only one deformation accessible to us, available to us. So let me just discuss what's going on locally. So locally, we can model this on C2, on Z2. So C2 is also a complex symplectic manifold with symplectic form dZ1, dZ2. And so I want to consider the orbifold of C2 by the cyclic group of order 2, which changes the sign of both coordinates. So algebraically, the quotient is the spectrum of the ring of invariant functions. And so what are the invariant functions? The invariant functions are the product Z1, Z2, Z1 squared, and Z2 squared. Right? So these are any polynomial in Z1 and Z2 which is invariant under the simultaneous changes of coordinates can be expressed as a polynomial in these 3 variables, but they're not independent. Right? So there is a relation. Namely, if I take the product of y, z, I get x squared. And so this equation describes a cone in C3, and that's why I drew this quotient is a cone. So this cone is the x squared equals yz in C3. Now you can essentially you can blow up the singularity and describe it as a so we can blow up and make it into the total space of O minus 2 bundle over P1. And so there will be a non-contractible two-dimensional sphere inserted in place of the singular point of the cone. But you can also do a complex deformation. And so complex deformation just one second, is the same thing, but if you look at it from a side, so to speak. So complex deformation is just adding a constant here. So this is now a constant, a parameter. Yes, what's the question?
Why are we making this blow up at 4 points? Why not make the total of the wave as equal?
So this is where so for the moment I'm just looking at the geometry of this space. I'm not paying attention to the function itself. The Weierstrass function actually is behaves differently at this different point at this point. So it is singular at one of these points and it's non-singular at other points. So indeed that's going to be important. But I just want to discuss how is it how is it this local geometry changes when we resolve the singularities. And so this is not a resolution, this is deformation. Now, if you think about this complex surface as a real four-dimensional manifold, you can actually, it has many complex structures. And so what looks like a blow-up in one complex structure will look like a complex deformation in another complex structure. And so from the real geometric point of view, these are all equivalent procedures. And so what this procedure does, it replaces this space by a new space. So now it's a non-singular quadric. So now we can look at this two form, which in these coordinates would be expressed as dy, for example, dz divided by 4x, right? And now I keep this form, but I deform the relation between x, y, and z. So now it happens. It turns out that this form has a non-trivial period. Because let me write this. Let me rewrite this equation as follows. Let me say x is zeta times little x, y is zeta times y plus square root of minus 1z, and z is negative zeta y minus square root of minus 1z. This is just a parameterization. So now this equation becomes simply that x squared plus y squared plus z squared is equal to 1. So it's the equation of the sphere, but it's actually it's a complexification of the sphere. So it's so there is a real sphere when x, y, and z are real, and so that's the non-contractible S2 which I promised. But since I'm just making a change of variables, x, y, and z have both real and imaginary part. So what displays? No, differential of omega is 0. Differential of omega is 0 because x, y, and z have a relation. So this is yes. Okay. So this form is okay. I will not be very specific, but it would look like dx dy dt over x. Maybe there are some square root of -1, maybe over 2. So now I claim that if I restrict this form on a real sphere, so this restricted on S2, which is defined by the equation that x, y, and z are real. This is just a volume form. Just a volume form on a two-dimensional sphere. Just write it. So x is cosine theta, y is sine theta, cosine phi, z is sine theta, sine phi. So this will be just the standard volume form. And so it has a non-trivial, famous non-trivial period, which is 4 pi, I guess. And so this form therefore has a non-trivial period proportional to zeta. Okay, so going back to this case, this example, n equals to 2. I want to do the similar analysis with this invariance, but now it's directly in the elliptic case. So if I have two variables p and x, but now x is elliptic variable, so it's defined up to the periods, and I want to make a quotient with respect to the symmetry. What are the invariant functions on the space? I'm allowing functions which have poles in x, otherwise we would be without functions because the elliptic curve is compact. So one function which is famously invariant under x going to minus x is the Weierstrass function. So it is. I should have written the formula, by the way, for pay. I mean, if we start with simplicial complexes, then maybe we need a formula for pay function. Yes. Because that's a symmetry. It's a symmetry of the Hamiltonian, and it's a symmetry of the symplectic form. There's also a constant which I don't remember. Plus a constant, which is usually chosen so that the expansion of this function near 0 starts at x squared term. So there's no constant term. So my Hamiltonian in this notation, the Hamiltonian is essentially p squared plus nu squared p function of x. And so it has a symmetry which changes the sign. The Hamiltonian itself, of course, has a symmetry which changes separately the sign of p and x, but it's not a symmetry of the symplectic form. We have a symplectic form. So if I change the sign of x, I want to change the sign of p. Otherwise, I'm not. Okay. So So let me call this function capital X. So this would be the analog of, I think, what I called Y. Now, there's another function. So if I take the derivative of the pay function, it is, so if pay is, since pay is an even function, the derivative is an odd function. So I can multiply it by p and produce another invariant function. So I apologize, it will be slightly different. Let me call this x1. Okay, let me call it x1. That I will call capital Y. And then there is another function, p squared. So let me call it x2. So here I got myself another three invariant functions, and every invariant function of p and x, which is meromorphic with respect to x, will be a polynomial in these three functions. But again, as before, they are not independent. And so, what is the relation between them? Well, let's compute y squared. So y squared is p squared times the square of the pay function. So p squared is x2. And the square of the pay function is a cubic polynomial in x1. So this is 4x1 cubed minus g2 x1 minus g3. So this function solves the KdV equation, which is when G2 and G3 can be explicitly computed so the way to prove it, you expand left-hand side and right-hand side and x near 0. You make sure that all singular terms agree, and then the left-hand side minus the right-hand side has no more singularities on x. Therefore, it's a constant. And if you adjust constant so that then this constant will be 0. So G2 and G3 are expressed in terms of the fourth and the sixth Eisenstein series. All right, so this is the equation which replaces the this quadric which we had in the local picture. And now, if you expand this cubic polynomial in terms of its roots, well, near each of the roots, you'll have the same story, and there is a fourth. So the fourth point, the fourth singularity, which is actually an interesting one for this system, is when x1 goes to infinity. So now so my phase space, if you like, so my phase space is a complex surface which whose affine part, so there is a part of it which is described by this equation, to the extent that this equation is not all of the elliptic curve. So the elliptic curve is compact, and this equation describes the complement to a point. So this is the algebraic curve. So I need to either make projectivitize this equation, right? Make it a homogeneous equation of degree 3, or just say that I'm adding a point. And so when I'm adding some points, I will partially compactify the surface, and the net result and this is where I'm actually heading, is that
So this equation for which very simple, and I think that curve will have if we have equation for two variables.
right. So this is a complex surface, right? So this is a surface. It's a two complex dimensional manifold, and I want to represent this two-dimensional manifold as a fibration over one complex dimensional base. So it's a base of complex dimension 1. Fibers, which will be also of complex dimension 1, and the fibers being elliptic curves. But now the complex structure of these elliptic curves will vary, will depend on the point on the base. And so I will just massage this equation so that you will see how it goes. Remember that we had the Hamiltonian. So the Hamiltonian H expressed in terms of my invariance is simply x2 plus nu squared x1. Right? So now I substitute this into the equation. So I say that y squared is equal to h minus nu squared x1. I put 4. And I'm tired of writing x1, so let me erase index 1. So now x is x1. So E1, E2, E3 are the roots of this polynomial. So just like G2 and G3 are Eisenstein series, E1, E2, E3 are some theta constants. They sum up to 0. So now think of this equation as follows. Let me rescale H and call it nu squared times U. So then this will look like 4 nu squared U minus X, and then this thing. And so when I fix the value of my Hamiltonian, of the energy function, the fiber, so this set of all points in the phase space which have the same energy, is a solution of this equation. And now this deformation / resolution consists of adding a point at infinity. So I'm just adding a point x going to infinity and y going to infinity as x squared separately for different u's. So I'm doing this. I'm doing the opposite to the I forgot what it's called. Reduced suspension, right? So no, I'm not okay. Not that opposite. Not that opposite. I'm making a refined suspension. Refined suspension. So I'm making a suspension, different suspension over different points on the base. Okay. So I'm come back to, okay, in other words, if I just take this the affine curve given by this equation, well, so y squared equals a polynomial of degree 4. You know that this is also an elliptic curve, but it's an affine curve, so it's an elliptic curve missing 2 points now. So I'm adding back in those 2 points, compactifying the fibers. So now the complex structure of this elliptic curve depends on U. It depends on the cross ratio . So it depends on cross ratio of U, E1, E2, E3. And so it will degenerate. There are 4 points on the base. If I compactify, I can compactify the base by adding a point at infinity. So that way I will make it CP1, and there are points E1, E2, E3, where my fibers degenerate. And so, so all this we see once we complexified the problem, because over different points the fibers degenerate in different ways, and you cannot see that if you only look at the real slice. And, elliptic curves behave in a kind of irregular way if you try to slice them on the real. If you look only on the real points, but once you complexify, everything becomes regular and beautiful. So the claim is that this structure persists for all n's, not just n equals to 2. But to see that, we need to describe the Lax representation for elliptical Legendre-Moser system, and it was found by Igor Krichyver in 1980, maybe earlier, but that's where it was published. And by finding this Lax representation, Igor actually discovered what later became known as Hitchin systems. And now, in the framework of these lectures, when things are related to gauge theories, I will present this construction as the analog of the construction we had yesterday for two-dimensional Young-Mills theory, but after we've complexified something. So let me proceed in this way. So I will claim that this is actually kind of a complexification of 2D Young-Mills construction from yesterday. So let me very, very briefly review what we did yesterday, especially for those who arrived later, and I will avoid unnecessary details. So yesterday, we looked at the following infinite dimensional symplectic manifold. So let me just call it P infinity. It was the space of pairs E and A, where E was the function on circle valued in this simple Lie algebra, or maybe semi-simple Lie algebra, and A was the one form, circle valued in also valued in Lie algebra, and multiplied by a finite dimensional orbit. So okay, so the Lie algebra was actually SUN. The orbit was the n-1 dimensional projective space, and we were performing a symplectic reduction by the action of the group, by the loop of the action of the loop group. So G is SUN, and loops here are again. So these are arbitrary maps of a circle into the group. These are not marked loops. There's no base point here, but the base point appears once I define the action of the loop group. So okay, let me just review the action of the loop group on this data. So G, which is G of X, so X is point on the circle, acts on the pair E A so this is just a piecewise, pointwise conjugation, and this is the gauge transformation of a connection. And now the point Z of the orbit is acted on via evaluation at the marked point. So now we need to mark a point. Maybe I was using inverse. So my circle now has a base point, which I call 0. And so the moment map for this combined action on the cotangent to the to the phase space and this fine dimensional orbit is the covariant derivative of electric field E plus delta function. So it's a distribution supported at this base point, and J is the finite dimensional moment map describing the embedding of Cpn minus 1 into the dual space of the Lie algebra. And this is where the coupling constant appears. So let me write explicitly what is J. So if I represent this point by a sequence of complex numbers whose norm is fixed to be 1, then so this J is mu times Zi Zj bar minus delta Ij. So this is it's a traceless square root of minus 1. So this is traceless anti-Hermitian n by n matrix, which is what an element of Lie algebra of SUN should be. So nu is gives you the scale of things, and so that's the parameter. And so yesterday what we found was that if you solve this equation and then compute the Hamiltonian, which is the integral of a circle trace E squared, this becomes the trigonometric Calogero-Moser Hamiltonian. So today we'll complexify. So I did not explain what was. So I said that Z2 complexifies into a circle, but I didn't say what the circle complexifies to. And so one way to complexify a circle is to make it in the elliptic curve. Yes. It's a point on the projection space. You see, O is Cpn minus 1. So it's a collection. These are n complex numbers. This is the equation they obey, and they're defined up to their overall phase. Okay. So this matrix is invariant under this overall phase rotation. So this is a well-defined embedding of Cpn minus 1 into the space of n-bind anti-Hermitian matrices. Yes. So this is all you need to know. So right. So the we derived it yesterday from a longer discussion, but this is all you need to know for the procedure. So we just solve this equation, mu equals to 0, substitute here, and you'll get the Hamiltonian. I want to generalize this now. Okay. Yes.
This location of the steady called Wilson law.
Yes.
And then the whole construction depends on this completion, right? Even if you have a circle both of them.
So you can, okay, very good point. So you can ask what will happen if you move this point in here. Nothing will change. So, but what will change things is that if you add 2 points, 3 points, so you can have many points, that will change the system. So this is what I said yesterday when you said it could have many lines. I mean, we can go there, but I want to briefly, explain how this is generalized in this case. So I want to replace the circle by an elliptic curve. So I'm fatten the curve. I mean, fatten the circle. And you have options how to view the analog of this phase space. So new phase space is now going to be the space of pairs. Okay, I'll call it E, even though usually it's called phi. So E will be now. It's a bit silly to be okay. So this is still just a function on. So this is a two-dimensional torus, which has a complex structure, but I'm allowing just arbitrary functions. Functions of z and z bar. So these are not meromorphic functions. Sorry, x, z and z bar. So let me distinguish. So the coordinate on this elliptic curve, the holomorphic coordinate will be z, will be denoted by z. So it's a function of z and z bar, function on T2, valued in complexification of my Lie algebra. So it's now valued in SLN-C, Lie algebra. And A bar will be the 0-1 connection. So it's so really this function is actually it's a 1-0 form, and A bar is 0-1 connection. On this become important when you generalize this to arbitrary Riemann surface. On elliptic curve, you have global coordinates. You have global one differential, so you can trivialize everything. But what's important is that the gauge group will act in a way which depends on the choice of a complex structure. So now I'm I will explain what this means. So I'm just complexifying ingredients and kind of making it much more expensive in terms of the number of degrees of freedom. Now, what is OC? So OC is a complexification of CPN minus 1. So so here we had Z, the vector, called Z vector. So Z was in C to the n, and as in Andrei's lecture, so Z was non-zero, considered up to the overall scaling, which I fixed partially by requiring that the norm was equal to 1. So now complexifying this means making Z and Z bar independent. So O of C is now the space of pairs. Z in C to the n, W in C to the n dual, in the dual space, such that the value of W on Z, so this is the analog of this norm, is equal to 1. Up to the scaling. So here we had U1, and U1 becomes C star. One way to complexify U1 is to make it C star. So C star acts simply by scaling Z and W in opposite way. Okay, so now we can define the analog of J. So make it into a matrix of the form ZIWJ minus W delta IJ times nu, maybe square root of -1, but it doesn't matter. So this is simply a traceless n by n matrix, element of the Lie algebra of SLN. And so now I want to make a group of maps of T2 to the complexification of my group. So the group SLN acts on this phase space, and it acts as follows. So I need to mark a point. Let me call it point z equals to 0. And so so now G of Z and Z bar acts on the quadruple E A bar and the equivalence class of ZW by, again, pointwise conjugation of E So here is where we use the complex structure. So we put here the Dalbo operator. So I'm only differentiating with respect to Z bar. I'm not touching Z coordinate here. And I evaluate G at its mark point 0. And this is how I act on Z and W. So, so the action at the orbit is by evaluation at this point. So now we need to compute the momentum map, and perform the reduction. Okay, I will do it here. By the way, we don't have a clock today. What is the timing? Perfect. Okay, so the moment map is, we will compute it maybe in the exercise session. So this is the complexification version of the covariant derivative of divergence of the electric field, plus the same delta function, but now it's a two-dimensional delta function. And so we want to solve this equation and divide by the action of the group. So how to solve this equation? Well, as yesterday, the trick is to find the representative normal form for A bar. So what is the canonical form you can make the 0-1 connection on a trivial bundle look like by performing the complex gauge transformation? So there is a theorem by Atiyah. So it's a kind of complexified version of the Floquet-Lyapunov theory, which says that the generic A bar, can be brought to the diagonal constant form, where alpha i's are now complex parameters and they are constants as Z bar are concerned. So there is a gauge. It's only true for generic A bar. So it means that if you pick one with probability 1, this is true. But of course, you might be unlucky. And if you're unlucky, then something interesting happens that you can always diagonalize it, but the diagonal components need not be connections on the trivial U1 bundles. So they could have non-trivial first-chain classes. So this is interesting for, actually this is interesting for applications in condensed matter physics, particularly related to the physics of graphene, but I will not talk about this today. Like, I just wanted to make Pasha wake up. Diagonalize means diagonalize. It means direct sum. It's yes, direct sum of line bundles. So it means that the rank n vector bundle of trivial degree, which A bar represented, generically splits as a sum of line bundles of trivial of degree 0. Okay, and these alphas are, so the alphas represent those line bundles. These are the stable bundles. These are ITR bundles. I don't exclude them. I'm taking them. I exclude not ITR bundles. Okay. What I said that it's not always true, but this is what I'm going to work with. What, sorry? Semi-stable. No, the semi-stables. These are semi-stable bundles because they have sub-bundles, obviously. So it's and they slope 0. So they all slope. This is slope 0, and the sub-bundles are slope 0. Okay. In practical terms, all I'm saying is that by complex gauge transformation, I can make almost every A bar diagonal matrix with constant coefficients. And as yesterday, there are remaining gauge transformations of the form, so these are diagonal matrices whose diagonal entries are now periodic functions of Z and Z bar. So how do you construct a periodic function? So you can either make a combination Z minus Z bar divided by tau minus tau bar times 2 pi I an integer. So this is invariant under the shifts of Z. Remember, we have shifts of Z by integer or tau times an integer. So the shifts by integer don't change Z minus Z bar. Shifts by tau times an integer will shift this whole combination by an integer. So e to the 2 pi I kills that. Or Z tau bar minus Z bar tau divided by tau minus tau bar. Question? No question. Okay, so these transformations will shift alphas by the Z bar derivative of that. So it will be 2 pi I tau minus tau bar Ni plus Mi tau. So it is convenient to introduce variables xi, which are tau 2. Remember, tau 2 is the imaginary part of tau divided by pi alpha I. So these variables will be defined up to the shifts by an integer or integer times tau. Okay, so that's just partially uses almost all of my gauge symmetry. Now we need to solve this equation with A bar of this form. So we do it analogously to the way we were doing it on the circle. So in the braces where A bar is diagonal, we look at the equations for the associated matrix elements of E. So when I is equal to j, the equation is simply that. So it says that the diagonal matrix element of E is holomorphic outside 0 and has only a pole of the first order. So the equation d bar equals delta function is solved by a meromorphic function of the first order pole. Now, this is the complexification of requirement that you have so this is it's a complex analog of the equation we solved, but maybe without paying much attention to it. So if you do it on a circle, the same thing. So you have so this is for comparison. You see, to have a pole in complex world is analogous to have a jump in the real world. So in the real world, this equation says that EII is constant outside x equals to 0, and it has a jump. So the value, let's say minus 0 and plus 0, is equal to JII. So if your function is a constant and has a jump, it means that the jump should vanish, right? So this is precisely analogous to the fact that if you have a function on an elliptic curve, it has only first order pole at one point. This pole has to be 0. The residue is 0, and the function is actually constant everywhere. So this is the complexification of that theorem. So JII is equal to 0, and EII, which I will call PI, is a constant. Okay, now let's analyze what is JII. So this is my matrix J, and so JII is square root of minus 1 mu times ZIWI minus 1. And so this equation saying that this is equal to 0 implies that ZIWI is equal to 1 for all I. And now, just like on the circle, we have one more remaining, not one more, but we have other remaining transformations when G is diagonal T1, Tn, when Ti's are in C star. Of course, the product is equal to 1. And so by those transformations, I can make Z equals 1 and W equals 1. So now, let's solve this equation when I is not equal to J. So now things are interesting, because now outside the origin, the solution for EIJ is simply the exponent. So it's minus Z bar alpha I minus alpha J. I can make it to make my life slightly easier, I can put it z minus z bar here, times some function, let me call it L, Lij, which is only allowed to depend on z. Now, this function should have a pole of first order at 0. So Lij should have the pole Jij close to 0. And it should also have now some automorphic properties that, well, it should be periodic with the shift of z by 1. And the shift of z by tau should precisely compensate the non-invariance of this exponential prefactor. So it should be e to the tau bar minus tau times alpha minus alpha j. Now, what is Jij? Jij, now that we simplified z, is simply square root of minus 1 nu 1 divided by z. So it's times 1 minus delta ij. Okay, so these three properties fix L uniquely, and that's the Cauchy-Lax matrix. So Lij of z up to, so it's the theta, it's the odd theta function. Okay, so just like Andre, I will not write the argument. I will not write the subscript. It's the odd one of z plus xi minus xj, where x is introduced here, divided by theta of z, theta of xi minus xj, square root of minus 1 nu, and theta prime of 0, to make sure that the residue is the right one. Okay, so the new phenomenon is now that unlike the trigonometric case, when we had the analog, so this electric field E, which when you solve for it, it has the analog of this exponential dependence, but the prefactor, which was responsible for the Lax operator, essentially had no interesting dependence on the position of the circle. Now this function has an interesting z dependence, which leads to the following beautiful fact that okay, so first of all, so if I now look at E, the electric field, and compute its Casimir, well, okay, so the electric field itself has both z and z bar dependence, but the invariant, so if I compute the Casimir, actually has no z bar dependence. It depends only on z, and of course it follows from this equation. But it has a pole, so it's a meromorphic function of z with now second order pole at z equals to 0. Now the space of meromorphic functions which have a pole of second order at one point on the elliptic curve is two-dimensional. So such functions, all such functions have a form, the Weierstrass function, the function times some constant, plus another constant. And so this other constant, so this first constant is computable and it's proportional to nu squared. And the other constant is precisely the Hamiltonian, precisely this Hamiltonian H2. So now, if we go back to the large phase space, which was the space of E, A bar, and so on, and start the classical evolution generated by the Hamiltonian, which is the regularized kind of averaged version of Tracy squared. So essentially the second order pole, because it is meromorphic, allows the integral, the principal value integral of Tracy squared to be well defined. You see the function, so dz bar over z squared. So the principal value means that I'm integrating over the complement of a small disk, small round disk. So actually it doesn't have to be round. So the fact that it has a pole is compensated by the fact that this, if I first integrate over the angles, I get 0. And so singular part disappears. And so this is a well-defined Hamiltonian, which defines a simple evolution on this infinite dimensional space of E, A bar, etc. And then we project by the action of the gauge group and produce the highly non-trivial evolution of this elliptical Legendre-Moser particles. So we can now exhibit the algebraic integrable structure of this phase space of the system using what we've learned, namely this phase space now has the structure of a fibration over n-dimensional base with fibers being abelian varieties. So these are the complexified, again, one of the possible complexifications of Liouville tori of real integrable systems. So what are these abelian varieties and what is this fibration? The fibration is defined as follows. We want to extract as much as possible from this electric field or from this Lux operator. And so the spectral invariance of this Lux operator will be conserved quantities, because on this infinite dimensional space, any flow generated by suitably regularized Casimir of the electric field will produce a flow which commutes with the flow generated by Tracy squared, because anything which is built out of electric field Poisson commute with each other. So these are commuting flows, and because we're reducing by the gauge transformations which don't touch the spectral invariance of E, so that's the source of conserved quantities and the integrals of motion. But now, because we got something which depends on a point on the elliptic curve, the spectral invariance vary from point to point. So the object which is convenient to study is the spectral curve. So this is the set, the vanishing locus of the characteristic polynomial of L of z. So it's a curve which lives in, so where does it live? It lives, so we have elliptic curve E. We have the bed point z equals to 0 when L has a pole. So that means that, so over generic point of elliptic curve, this equation has n solutions. It's time, okay. But over point z equals to 0, something happens because L has a pole. And so, but the residue at this pole is the matrix of a special form. So it's a matrix which has, it's a difference of the scalar matrix and the matrix of rank 1. And so if you shift, well, there is a way to, okay, I will not say it in full detail today. So there is a way to partially compactify. So this curve sits in the partial compactification of T star of E minus the point. So there is a little bit of blow up you need to do to resolve the structure near z equals to 0. And the point is that this is, so the claim is that this is genus n minus 1 curve, which covers, essentially covers the elliptic curve. And so the Jacobian of, yes, sorry, and so it depends, so this polynomial, so this is a polynomial of lambda and the meromorphic function of z. So it's so as a polynomial, it has n minus 1 non-trivial coefficients. Each coefficient is a meromorphic function of z. There are only so many functions with the singularity at the point z equals to 0. So you can count how many parameters you actually have, and you get precisely n parameters. And so let me call them collectively u. So u. So these are the coefficients, the free coefficients in this polynomial. And so for any value of u, you have a specific curve, and its Jacobian is essentially the fiber of this fibration. So this Jacobian has it already has genus n minus 1. So there is one more missing, 1 degree of freedom missing, which is the elliptic curve itself, and that which corresponds to the center of mass, which we discussed earlier. Okay, so this is only one of the many examples of integrable systems which have a lax representation with the spectral parameter, and so I gave, in this case, I gave a gauge theory description of that. The other systems, which for example, the base curve, instead of being elliptic curve with 1 point, is genus 0 curve with many points, are also possible, and they are the complexification of the system, which you will get by marking several points on the circle. So starting the day after tomorrow, we will be describing a completely different story, which will start as a different story, which with origin in gauge theory, but the endpoint will be exactly that structure. So we will recover these integrable systems, both classical and quantum, from doing something like probability theory on some finite, or infinite, but filtered sets, and the asymptotics of the expectation values in this probability problem will be described by this system. Okay.
So questions?
Once we have this yellow formula on the board,
Yes.
so you could always stress the fact that this is elliptic genus is somehow connected. But I never figured, I guess I don't know what is the.
Yeah, let's try to ask this question on Thursday, maybe. Yeah, maybe we'll get. I mean, sorry. So the story which I will the story which I will present will recover this as a result of doing some limit shape computation in ordinary cohomology theory. So this is not related to the elliptic genus. So at least in the story which I know. So that story which I know has the elliptic version, but that ellipticity goes into the direction of the double elliptic system that Colli mentioned. So you see here the fact that the P dependence is rational has to do with the fact that this is related to the cohomology theory. If I go to K theory, the P dependence will become trigonometric. And if I go to elliptic, the P dependence will become elliptic. But actually, calling this double elliptic is actually the wrong name. So people, I mean, I'm partially responsible for that. The truth of the matter is that once you start making both the fiber and the base elliptic, it's very hard to keep track of who is fibered over who. So in the simplest case, already the system of 1 degree of freedom n equals to 2, it turns out that the total space is the abelian variety, which is the Jacobian of a curve of genus 2. And so you can locally think of it as describing the fibration of one elliptic curve over another elliptic curve. So it has the moduli of both elliptic curves and the point on one of the curves, which describes how you shift over one curve and going around another. But it's not a globally it's not a global description. Globally, it's just the period matrix of the genus 2 curve, and which kind of emerges out of this structure. So it's and that's to be expected for high n as well.
Could you please repeat why a diagonal part of E should be constant?
Okay, just try to find the elliptic. Try to find the meromorphic function of the elliptic curve with a single first order pole. Yes.
So is this moduli space exactly the Hitchin moduli space on an elliptic curve with puncture?
With one puncture.
With one puncture.
With one puncture, with one minimal puncture. Yeah. So technically, it's a minimal puncture. So the fact that the residue of L at this point is a scalar minus rank 1 matrix means that's what it makes it minimal.
For GLN, right?
Practically, Hitchin system is for any L over not elliptic curve, or curve of genus 2 and higher.
With parabolic.
Not practically, but technically. That's what Hitchin invented. But if you think, if you understand that Hitchin systems live in families over the Deligne-Mumford stack of curves, once you start degenerating curves, you will get curves with punctures of lower genus, and that's what that's just. Okay, interesting things happen when you impose restrictions, right? So so if you so if you make J a generic orbit, then you will get L, which will have this factor, but it will also have a dynamical prefactor. So you will get what is called a spin Calagione-Mozart system. And I mean, there is still some mystery here, which is what that Alshonetsky and Perelomov discovered, that the systems make sense for any root systems. And of course, you explain this using kind of sophisticated algebraic structures. But there is no Hitchin system which will, so if you try to generalize this to other simple Lie groups, there are no orbits which will explain the Lax operator for other root systems. So Hitchin system is not the end of the world. So I put it this way.
Okay, more questions? I have a very short question. So there are these special connections that you threw away. When you modify this phase space,
Right.
just as you did at the beginning, does it mean that you add them back?
You add some of them, yes, precisely. So in order to make the fiber compact, you need to allow for the situations where in the usual physics language, some of the particles run away to infinity, or they run through each other with infinite speed. And that is described by allowing for unstable bundles. So then what happens is what plays the role of the coordinate, this coordinate, actually loses its meaning because the associated component of the gauge field A bar now becomes a constant magnetic field gauge field. So when you have a magnetic field, it means that this alpha actually now has a z dependence. It has a linear z and z bar dependence. The zero mode, which alpha is, no longer has a meaning. So I don't have the complete story there, but it's just the beginning.
Okay, thank you. Thank you.
I just mentioned something for Pasha. This is stable things are related to what's called magic angles. Twisted bilayer just.
Войдет в зал, да? Алло. Это еще что такое? А не та старая?
Что вы делаете?
Не та. Все понятно.
Нет, так,
Вот это.
зачем трудно?
Все. Ты сейчас помнишь, как мы... Пардон, я уже включен. Ну, так сказать, одна минута.
Алло. Слышно, да?
Слышно. Слушай, мне нужна помощь небольшая. Почему на эту кнопку нажимаю? Переключать страницу. Ага. Ага. Подожди. Нажми на кнопку, и начинает переключаться страница. Ага, нормально. Нормально. Сейчас проверим здесь.
Работает?
Работает и так. Здесь немножко точнее.
Okay, it's my pleasure to introduce Professor Ivan Cherednik, who will speak about Q-Zeta Revisited.
Thank you. Thank you very much. So this is the... So this is the plan, abstract actually, right? So this will be the main point. A questionable, I know, why complex S have generally no direct arithmetic and geometric meaning here. But in process, what is superduality? There is no Nikita here. For instance, for Nekrasov's instance terms, it is epsilon 1 transposed with epsilon 2. Something which many people know, mathematicians, especially physicists, actually. This I will explain, of course, carefully. And then in process, I will define, I promise, I will define elliptic whole polynomials, and then I will need this mysterious column here. I will explain later. Okay, so we're done with this, with the abstract. And let me go back. I need to explain a little something about the main point of this talk, of this lecture here. Definitely I need to do it because this is a little bit non-traditional, softly speaking. Okay, so what about zetas? What is the meaning of this question? Are zetas geometric and arithmetic here? What we know about zetas, so of course there are two main examples, classical Riemann's zeta, something which I am doing almost full time here, Hasse-Weil zeta, mod p, algebraic geometry mod p here. But the closest to my talk are Selberg's famous celebrated Selberg zeta, the count of closed geodesics, and the so-called spectral. Spectral one is very simple. Give me any operator, and I will put calculate its spectrum if I can. Sometimes it is difficult, of course, you know, right? And then I will form this spectral zeta. There are interesting connections, really very interesting connections. But on the other hand, let me focus on applications. Okay, good. Let's discuss spectral zeta. For instance, you want in any universe, let's consider Igor's universe, Igor's world. His works here, right? Let's consider, for instance, Riemann surfaces, Kp, and so on and so forth here. Theta functions of Riemann surfaces. But with whatever approach, still one of the key questions is to calculate the determinant of the Laplace operator. A version, a determinant of
the determinant of any first order operator, Dirac, for instance, operator, and so on here. Okay, surprisingly, still surprisingly, the best known way is to introduce zeta, exactly this particular zeta here, and then to do this formal combination. Minus zeta prime x here, then extend it analytically to complex S's with some regularization, tend S to 0, and here you are, you will get determinant. Of course, in Igor's universe, so to say, right, there are possibilities to use quasi-periodic solutions, finite zone solutions, and so on and so forth. You can use it, right? But this is the most universal method which works practically always, especially with some latest theories and some exotic theories. So surprise, surprise, the simplest way is to introduce zeta, extend it, now spectral zeta, extend it analytically to complex S's, and then tend S to 0 here. Here we are. Then pretty much the same can be done, but this is non-trivial, with Selberg zeta. Selberg zeta is much, much easier to calculate, actually. This is complicated. Even for when lambdas are 1, 2, 3, n, there are quite a few operators with such properties. Still, you know, you have very complicated analytic number theory. Okay, but in one instance, let me just attach it, or something like this, right? It is really pure pleasure to calculate Selberg zeta here. Let's consider some special curve, which is h divided by gamma n. Gamma n is classical congruence subgroup. It can be SL2Z, but sometimes compactification is necessary. But let's just divide by gamma of n here. Okay, perfect, right? And then there is a famous celebrated Selberg's conjecture. Selberg, by the way, himself proved functional equation and Riemann hypothesis for compact Riemann surfaces. And he conjectured then if it is if this particular X Riemann surface is of arithmetic nature, then lambda 1, the smallest eigenvalue here, is greater or equal than 1 over 4. Himself, and then a bit later, people immediately realized the connection with so-called Grant Riemann hypothesis. If lambda 1 is smaller than 1 over 4, then immediately there is a counterexample to Riemann hypothesis. So close connections, but of course they look somewhat mysterious, right? Not only for those who see it for the first time, including myself, by the way, but even for specialists. We don't know, we don't understand how it works, but of course we have a lot of implications here. Okay, a little bit different example. Now Nikita is here. Ising model with external magnetic field. So this is, so to say, integrable universe, right? Now it is famous, or better to say infamously non-integrable. Ising model is integrable when d equals 2, of course, right? With d equals 3, we know. But when d equals 2, right, but still you add external magnetic field, many people tried, including my friends, and no way, it is non-integrable. We have solid evidence now based on effort and time. People spend solid effort that is non-integrable. Perfect, but still for any d, we have Lee-Yang theorem, the corresponding partition function in terms of complex fugacity. Fugacity is inverse time multiplied by Boltzmann constant and inverse time and then multiplied by h, of course. External magnetic field here. Okay, so in terms of complex fugacity, it satisfies Riemann hypothesis, surprise, surprise. Now it will be unit circle, but this is equivalent for any d. Then conclusion. You consider log Zn, Zn it is not physical, of course, n is the number of particles, so to say. Then you tend standard combination, log Zn divided by n goes to infinity here. This is physical now. And then you prove in some very strange way that it has no unwanted phase transition. So you have circle intersects with real line at one point, here we are. Very strange, very exotic way to prove that it has just one phase transition, no unnecessary conditions. Then I played mathematically with this. I deformed this theory, I will not explain how. And then I found that for some parameters, when fugacity, E to fugacity becomes complex here, not complex, negative actually, negative, right? I found that still Riemann hypothesis holds until some moment, right? And at this moment, or a little bit to the left, you will have not just some unwanted phase transitions, you will have the whole segment of phase transitions. So the theory is definitely not, Nikita, you are laughing, right? This physically, it is nonsense. This is okay. This I can survive. Yeah, I suspect there's some physical whatever arguments, right? So far, makes sense. It makes sense, right?
Yeah, but what's strange to me is that the circle intersects the real line at one point.
Guys,
How-
whom?
To me, Vanya, to me.
Oh. I try. Go ahead.
How can the circle intersect the line at one point?
What? Unit circle, phase transition by definition can be only real, physics theory, you know, right? And then unit circle intersects with a real line here at point 1. Positive.
Okay.
Thank you. Positive, of course, positive, right? Okay, so interesting story, non-integrable. But let me very briefly, I don't understand quite a lot here, connect it with the beginning of the story, Selberg zeta here. So story is more or less like this. If you consider, just a second, Anton, doesn't work, but anyway, doesn't matter. The light, but anyway. If you consider Selberg zeta, right? Good. Yeah. So just to help you to understand what is doable, what is not, let's consider Selberg zeta for this particular example when it is divided by SL2Z. Then immediately you will prove that no need to calculate the lengths of geodesics. You need only to calculate the norms of hyperbolic elements in this particular group. Exactly, the length is something like lambda squared. Lambda squared is eigenvalues will be lambda to minus 1. Take the greatest one, lambda squared, right? So perfect. This combinatorial problem. So Selberg zeta in this particular setting connected with Ihara. I will skip the definition. Ihara's zeta function and connected with a lot of zeta functions associated with trees, with graphs, and with whatever here. And now it is connected with partition functions, right? At least morally. Okay, so there is a connection, but of course it is not clarified. Okay, anyway, my conclusion that whatever you are doing, right, you consider zetas, you consider them, you extend them analytically to complex numbers in this example, and then eventually you need to tend S to 0, or in arithmetic consider some other remarkable real values. So we don't, conclusion, right, questionable conclusion, so we really don't understand what is 1 divided by n to s. Right, because of S, of course we understand, but when S is a complex number, this is quite a problem. So the best way I know by now is to replace it by some invariance of length spaces here, which are very much geometric. You will see. Okay, so we're done with introduction. I already spent by like 5 minutes. Okay, let's move. Right now it will be pretty much from scratch. What does mean from scratch? You don't like n to s, right? Try to generalize. So replace it. So what people did, the natural thing to do is just to replace it by q binomial coefficient to s here, right? Q binomial coefficient simply replacing n by sine h of x, n, something like this. But this is not exactly what we are going to do. We are going to fix n to s when s is a complex number. But still, people do this, and at least they proved that the limit is correct. The limit when q goes to 1. But we will do something different. We will use McDonald's measure here. So in a moment, you will see why McDonald's measure is a quite natural solution to the problem with complex powers. Look at the definition of complex power, what I already mentioned a couple of times. We're not happy, we're not happy with this particular formula. Look, just to divide u to s, you need a cut off, and then you need this combination, right? Moreover, if it is polynomial to s, it is quite long story, Bernstein set of polynomials, etc., here. This is simple, but still some unpleasant thing. Of course, classics of 19th century liked it, but not us. We don't like it because you immediately need at least some cutoff. You need to do something. Okay, so what is exactly the connection with n to s? Here we are. Stirling-Mock limiting formula here. Do exactly the following. Take this particular guy, then plug in, because of some renormalization reason, plug in square root of 8z here, q, and here we are. It will be minus z to k. So,
what's cheap? You need to define h to the k, not to define c to the k. What's the point?
the point is that this is multi-valued and this is single-valued. In Q calculus, there are no multi-valued functions here. We use this combination as the closest. Gammas are perfect, you know, right? But complex powers are not. So this is single-valued function with some singularities, but this is okay. This is Q gammas. Q gammas doesn't matter, they are single weight. In Q calculus, there are no multi. And with this we don't like, and seriously, people didn't like it even in the 19th century, specialists in zetas and similar stuff here, because it is multi-valued, right? Multi-valued are fine with Riemann surfaces, right? Inevitable, but not here. Here you have lots and lots of problems. Okay, so here we are. Problem, right? Complex powers are multi-valued. Solution. Do exactly as I explained, use A, right? Then, of course, there is a classical stuff, which is absolutely necessary to mention. This is classical story when that Q gammas, this combination of Q gammas here, goes to gamma. Then why we need this combination? Because if you don't use combination, there will be log term. There will be some expansion, right? There will be something in the beginning, then dialog, right? Which we don't want here. And then, so you need to consider this particular very smart combination. The numerator is simply theta function, actually. But this is not theta function because it is plus Q, plus K, and plus K2 times here. This is called truncated theta. Perfect, right? Then you do the following. You follow when Nishizawa here, you just consider delta minus S, etc., very simple to define. And then you'll have the second major feature of Q calculus. This function, just the definition here, will have dense everywhere set of poles, but otherwise it is perfect smooth function. If you approach any irrational or transcendental function, it will be nicely defined. In my programs, I use the test of three points here. I consider 3 points, right? And take 2 when the values are as close as almost coincide, right? So what is the trick? The trick is that when you approach transcendental function, the corresponding residues go to 0. Poles are here, but residues go to 0. Another, I decided I discovered some exotic examples, but then later I found that these exotic examples are pretty much common here. It is, we have lattice with 3 generators. So in this particular definition. But of course I don't like it, and then of course I will immediately switch to integrals. With integrals, of course, there will be no some such exotic features. Okay, here we are, Q zeta, but first let me discuss what I'm going to deform. This is basically zeta, but not exactly as you see, right? It is plus zeta, actually the simplest L function, right? This is actually eta function, but I will discuss eta function a bit later here. Okay, so this is from the second proof of functional equation, Riemann's proof, right? So here it is, right? Consider the following integral, classical stuff here, and they will get exactly zeta corrected by gamma and corrected by this factor, which is the price of plus here. If there is no minus, if it is minus instead of plus, it will be just zeta multiplied by gamma. Okay, and my formula is here. Now you understand perfectly that I placed x to k by delta k, right? I integrate. Now in the imaginary direction, there are 2 theories, not one. Here does matter, but here we have real, the so-called non-compact theory and compact. This is compact. This is integration in imaginary direction. Here we have the definition. Immediately the theorem, right? The limit is just fine. Consider Q. Q goes to 1, A goes to infinity. So here, why is this so strange? But it works. So far it works. Okay. Later I will ask Vanya, but no, not now. Okay, when A goes to infinity, meaning Q goes to 1 here, right? So the limit is fine. Everything is just for absolutely arbitrary. Anyway, I need to describe. Non-arbitrary, I will explain. Okay, so immediately there is a warning. What happens if you take here minus? Then we have something interesting. So, okay, let me try what Vanya explained to you. Maybe here, right? It's strange. Okay, let me just do it here. Okay, if you do it with minus, aiming at zeta here, then it will, apart from critical strip is S equals K plus 1/2. It is clear here, right? Then apart from critical strip, it will go to zeta. But inside it will go to some function which is essentially gamma. There is a phenomenon which is called as a phenomenon, maybe I can skip it. Okay, let me skip it. There are some interesting implications in analytic number theory of this very observation here. Okay, perfect. So let me skip it. Let me go to the next page. Okay, warning, simply warning, right? Be careful because with plus convergence is granted, but if it is not, then you need to do something. Okay, so here we are, the first point. Then phenomenon, which is the end of the problem here. The problem is that there is a strong tendency, almost Riemann hypothesis, the strong tendency for the zeros to go to the left. Very strong tendency. If all zeros of QZ go to the left, then it is the end of the story. It is the proof of Riemann hypothesis, of course, right? But this is just a tendency. Moreover, if you do it systematically, you will calculate the first derivative. The formula is here. And then you will see that for the first time, this thing is negative. Anyway, for the first time, the linear approximation go to the right is 1977-27, which is a famous zero of zeta function, exactly when there are two very, very close neighboring zeros here. There is a standard fact from 19th century that if the zeros are very close, a critical line here, very close to each other, then it is counterexample to Riemann hypothesis. So here we have the first suspicious pair of points. So this is pretty much perfect. Makes sense to specialist analytic number theory. Okay, so here we are, right? Unfortunately, it is absolutely impossible to calculate practically QZ in this business, but I will discuss the examples when you calculate it much better, much faster. Okay, so here we are. But first version of Riemann hypothesis. First derivative is no good at 1977 here. But on the other hand, there is no theorem that the whole Taylor series converges, so probably the second derivative will correct it somehow. Anyway, we don't know, but the evidence is that the track is right. Then let me do the following. I will not discuss Rogers-Ramanujan identities definitely today, but there is interesting. Rogers-Ramanujan identity occur when when real part of K goes to plus infinity. Then upon some modification, this thing is actually Q modular function. But this I am going to skip. Okay, so let me skip completely this theorem, right? But on the other hand, still, you see derivative can be calculated. Very interesting derivative. All values of zeta in this derivative, in this particular derivative, all of them are apart from critical strip here, which makes perfect sense. Okay, let me go to the next. I'm saving time for this column. Sorry, guys. Just skipping something which is not absolutely necessary. Okay, perfect. Analytic continuation. Now the business about analytic continuation. This is interesting. So then it makes sense to switch from delta function to so-called truncated theta function, which is mu. Mu stays for measure, for McDonald, for whatever, and it will be measured, right? Pretty much the same story, but on the other hand, still you will notice, like in theta function, you will notice +1 here, right? So this is exactly the difference. So now numerator is really a theta function. And here we have not theta function, but again, let me repeat it. If it is k here and would be minus k here, then it is theta divided by shifted theta. But this is different. This is just combination of Q gamma function here. Okay, so then basic examples. Now I'm going to integrate with this measure. Capital F here, so it can be Gaussian, it can be Gaussian multiplied by reasonably good Laurent series here, or it can be something which I need for zeta, E minus and E plus. E plus will be our main guy. Okay, so the theorem, now it is about analytic continuation. So if it is about this particular integral, right, it is analytic, and of course convergence is granted to zeta here, only in this range. Real part of k must be greater than some small negative number. Positive real k's are perfectly okay. Okay, so why? I already mentioned that there are no multiple varied functions, all functions single varied. Why I need to do anything? Why we have some problems with this particular one? Very simple. We have vertical integration path here, and then we need to avoid exactly this bad case, are exactly this particular C is the integration contour here, shifted in some negative direction. Exact calculation. So anyway, you cannot go through the wall. Walls are exactly here, right? So you have walls, but fortunately all of them are belong to negative part here. If you play with epsilon, you will see optimal. You will find optimal epsilon here, which is 1/4. We're doing A1 by now. No arbitrary roots. So So perfect. So two comments here, right? This is just about the limit to gamma function here. So we have analytic attenuation, the technique of analytic attenuation, and then we have straight analytic function, straight analytic integral. When real part is greater or equal than -1/2, then S is k plus 1/2. So we covered critical strip. Then I will show you how it works for arbitrary systems. You will be really surprised, I believe. I was surprised. I found it recently. Okay, let me go to the next page. So what is the meaning of this page? So now we understand that integral nicely behave. This I decided to skip before here. Nicely behave when the real part of k is greater or equal than -1/2. And then there is a technique of analytic attenuation, which is essentially picking up the residues. In Q calculus, any integrals can be calculated as sum of the residues. So it is pretty much what I am doing in my papers, including the last paper. Okay, now let me show you something which is much nicer for practical calculations. So let me replace the imaginary integration by the corresponding real integration. This is exactly this particular shape, which is shown graphically here. Classical stuff here, right? And then it is well known that you will get analytic function or meromorphic function anywhere, right? This is exactly what I'm doing. Let me try to adjust this. Oh, here it is, right? You see some kind of sign of this particular contour, right? From infinity minus epsilon I, epsilon is a small number here, to infinity plus epsilon I, right? Classical contour of integration. So you integrate, and then you will immediately calculate, you just Cauchy theorem, nothing else. You will get this nice formula here, which is extremely good even when A is like 750. You remember, Q is e to -1 divided by a. So it is very close to 1 here. Still, calculations are very fast, very reliable, unless it is about big imaginary parts of k here. So this is exactly the formula, which is a sharp zeta function. A bit later, it will be a Jackson integral, Jackson summation, but later, not now. Perfect. So here we are, pretty much a counterpart of the previous year, but now it is real theory, real integration, right? Here we have the limit. The limit can be calculated. So far, so good. And of course, the formula is real nice now. Much you don't need to calculate. And then, of course, it is real integration. Real integration is just the other way around. Zeros definitely prefer the right-hand side. Look at this particular picture, right? This is sharp, this is zeta. This is sharp. This is the first example, classical 14.13. Classical first zero of zeta function. A is big enough, 750. So then here we have classical stuff here. First, of course, we have this one. Then we have 21, 25, etc. This is exact zero of sharp zeta, and this is linear approximation. Good, but of course there are no theorem, and I don't expect any theorem that the whole Taylor theory converges. Here, somehow about 88, of course there are some discrepancies, but still linear approximation is good enough. Okay, but anyway, the point is clear. Zeros definitely prefer now the right half plane. Half plane here is very easy to control. K is better than S. K is 0. Critical line is real part of K is 0. Okay. Then we are approaching actually almost the end of this part of the story. Then I'll skip to revisited part. So Riemann Q hypothesis. So we are already reasonably happy, at least I was reasonably happy, with the statement that zeros go to the right, zero goes to the left. Sarnak in one of his papers mentioned that actually we don't need Riemann hypothesis. We need only the fact that there are no zeros in the right half plane. In one of his papers, he mentioned many things actually. But Peter wrote fantastic papers about this stuff, including for Selberg zeta. Read his notes actually, right? It cannot be better. And anyway, Peter Sarnak mentioned this is exactly what happens. So we have some theory when zeros definitely prefer the right-hand side, which is the end of the story, of course, right? But unfortunately, we don't know how to prove it, but this is what any reasonable person can expect. Okay, now I'm showing you Dirichlet function, the passage to Dirichlet function. Definition is very simple. This is Dirichlet function of conductor 3. Right, classical stuff, recalculated to k, not to s, but recalculated to k. So here we have pretty much the same sharp Dirichlet function, some remarks about the convergence rate, and then good news is that the first bad point when derivative is not to what we want here is only 246, not 17 something, 1700. So this is basically can be calculated, but I didn't retry it. So it appeared to be difficult, but still doable with good computers. Still, it is doable to understand what do we have. Is it really like some kind of conjecture? Do we have a conjecture? If at 246 0 goes to the left, the end of the story, we need to use something else, right? So perfect. This is when how to go to L functions, which is of course valuable itself here, and then of course what can be expected, right? Let me show you what can be expected. Now let's try to attack the true Riemann hypothesis, which is about that all zeros belong to the critical line. Critical line here again is k equals 0. Real part of k equals 0. Okay, let me show you calculations. So far so good, right? But of course, the range is not what Adlishko can reach or whatever. He can reach easily millions here. For this particular business, I reached only some modest values. But still, you see, pretty much everything is okay. But anyway, basically, let me just show you this picture. Right? Let's enjoy it for 2 seconds, right? And then let's go to the next page. This is the reference of the original paper. Good. So now we're going to revisit part, and now I have time, almost certainly I have time for many, many things, including elliptic-Hall polynomials. Okay, so the first point here is Q Meta-MacDonald or Cherenik-Meta-MacDonald formula, which is difference counterpart of famous Meta-Gauss integral formula. Okay, I need to introduce the same mu, actually, right? But now it will be for arbitrary root system. You can see here, oh no, it's not, maybe it was not because of me. Here it is, right? This is now standard stuff, arbitrary root system, but reduced root system, reducible use here. Here is the general definition. Pretty much the same material you see, right? Shifts by J, but this is general version when we assume that there are 2 lengths. Concerning lengths, now it is MacDonald-Daha theory, right? And I need to say something about parameters. Maybe now it's about time to say something about double-affine Geek algebra, right? So what is this particular guy? This particular mu function makes basic operators of double-affine Geek algebra unitary, right? This is the claim, but now let's discuss parameters. This is interesting. So first of all, we have Q because it's different theory. Then we have T because of these translations. Here you have, right, some kind of guys here, T parameters here, some new parameters. Am I right? Maybe I skipped something. So first, of course, it must be multiplied by, T is here, perfect, T is here, right? So we have Q parameter and we have T parameter, right? What else? If it is not ADE, then we have 2 T's, 1 Q. But we can move up to 1 Q and 4 T's, which perfectly matches famous beta-type Selberg integrals, which contains 5 parameters here. So we managed, so to say, right? We have some kind of sample, classical sample. Selberg was absolutely fantastic mathematician, of course, right? He provided us with this 5-parameter deformation of beta integrals. Here we can do it. Basically, we can do it now. Okay, so this is exactly about k long, k short. We have 2 roots, 2 types of roots here, 2 lengths, short and long here, and this is a general formula for long and root. T alpha means it depends only on the length of the root here. So here we are, mu function, which makes operate. What is Daha? Can I give a definition? Yes, I can. Daha is a universal deformation, 2-parametric deformation of Heisenberg, or 1-parametric deformation of Weyl algebra. Weyl algebra, to be absolutely exact, extended by Weyl group here. So the mathematical theorem, and not a difficult one due to Aleph company here, that they can be locally, they can be only deformation with 2 parameters. There is nothing else, right? Then a bit later we understood that Daha provides universal formalism for practically any Fourier transforms, not only those in terms of spherical functions, all of them, right? Verlinde transform was a confusion. Of course, there are some Fourier-Mukai transforms from algebraic geometry which are different, but all other Bessel functions, hypergeometric ones, all of them, right, were supposed to be covered, right? And this is exactly the confirmation. This table is classification. Anyway, what is Daha? Universal deformation, 2-parametric only 2 parameters are possible unless we do some exotic root systems here. Universal deformation. So pretty, they say, I mean, my predecessors say, Fock representation, I use the same words, but for me it will be called polynomial representation, representational around polynomials. Then if we go to elliptic level, I will say something about elliptic homology, then it will be so-called Layenha polynomials, which are serious here. That's it, right? There will be polynomial representation in Lyapunov functions. Okay, otherwise everything is absolutely okay, pretty much the same. So anyway, VEC with VEC here in Daha theory is called co-invariant, right? Again, just different terminology. Perfect, right? And then now, let me explain this point. I have time for this. Let me explain that Nikita somewhat simplified his life. Actually, he knows, of course, perfectly that there are 9 theories, 9 quantum many-body theories. Now I go to something when I cannot use this guy here. Look at this particular column, right? This is diamond, right? The claim is that we have absolutely all integrable quantum many-body, nothing else, because Daha is a universal deformation. First. Then we know from soliton theory, including Igor, we know that the most complicated representation of the zero curvature are elliptic. There is nothing else, right? Then there are many, many, many instances where elliptic curves are. So, by the way, Daha is directly connected with elliptic curves. It is based on fundamental group here of elliptic curve with one puncture. This is basically it is Daha. Then in post-quadratic relations, you will get Daha. So anyway, elliptic, elliptic, elliptic everywhere, right? And there is no escape. But there is something interesting I will show to you. So this, what is exactly how to read this particular diamond? Very simple. ER functions are elliptic, operators are differential, rational, differential, right? What is Macdonald theory? 3 of them have special names here. Macdonald TT. Functions are trigonometric, Laurent polynomials. Operators are trigonometric, meaning difference operators, right? Then RE, functions are rational, and then operators are elliptic. P function from Nikita's lecture here of ddx here, whatever it is. Okay, so what do we have by now? So check means known, known, known. ER and ET were defined in my papers here. Only Daha was used. No toroidal algebra, no elliptic algebras, no nothing, literally, you know, right? Then TT is, of course, well-known track here, Macdonald, right? Best of RR. Operators are rational, functions are rational, Bessel functions, to be more exact, multi-valued Bessel function here. And then let's approach to the bottom. What is the bottom? ET, let me spell it. Functions are elliptic, operators are difference, relativistic in Nikita's lecture here. TE, same, but functions are trigonometric, operators are whatever, right? Dot and dot means that definitely we know these guys here, because general stuff here is that there is Fourier transform. ER and R connect with Fourier transform. Fourier transform is a tricky thing. There are books and books even about classical Fourier transform. There is something to do here. But still, first principle, this Fourier transform connects the corners here. So this theory and this theory connect by Fourier transform. Of course, it is well-known Harish-Chandra theory about the first line here. TR and RT are connected by Fourier, which is Harish-Chandra Fourier transform, actually, right, with some extra parameters. Okay, now let's approach this particular block. Here dot means that nobody did it, actually, right? But this was done, at least theoretically. With ER, it is much better. I calculated a lot. So here we are, right? So the ultimate theory, elliptic theory, right? Operators, functions are elliptic, operators are elliptic, right? Problems with convergence, anyway, most formally you can put write something, but it will not work. It will diverge everywhere, you know, right? What is the name of this guy? Physical name. X theory, D equals 6. Here, presumably it is D equals 5, Bogomolny equation, what Witten did here. Presumably, with D6 it is, I need to explain. But X theory is pretty much obvious that we need to call this guy X theory. X theory from physics, X theory.
What is X?
X, it is called X, unknown, whatever, mysterious. Awful, right? D equals 6. Okay, we'll discuss it later here. But anyway, in physics, it is really elliptic. Good. This makes perfect sense. So good that I deleted this. It is from our joint proposal to whatever. Not my name, actually. Mina, some people. Anyway, it doesn't matter. Forget it. D equals 6. And this is the level of D equals 5, presumably. Bogomolny equation, what Witten likes, actually, right? But anyway, something like this. But this is question. This is ultimate theory, right? And here you agree, elliptic is supposed to be the last, with one reservation. So if Q is a root of unity, you automatically in this table, you go to the next level. rules of unity provides, for instance, if you want to go from trigonometric to elliptic, consider trigonometric at rules of unity. You will get, essentially, you will get elliptic theory. So maybe there is one more possibility. Elliptic at rules of, and Q is the root of unity here. But there is nothing else, right? Because of multiple reasons, we expect that that because of this fundamental principle, there is only one deformation of Heisenberg, which is Daha, universal deformation is Daha, and because of other instances here, right? Integrability stops here, but on something begins. This story begins here, non-integrable theories. Okay, so this, and then let me say something about cosmological connections. Many connections here, definitely. Flavors, I don't discuss flavors, is one of the flavors here. Q can go to 1, T can go to 0, infinity, many of them. Many flavors here, but this is interesting, right? Let's look at the middle, for instance, block here. So here, if you read it cosmologically, it will be elliptic cosmologies of G over B, classical flag variety, is connected, actually isomorphic, but you need to do something here, of course. K theory, which is trigonometric cosmology, right? K theory of G over B hat, trick, right? If you continue, you will get regular cosmologies of elliptic configuration space, right? Of elliptic configuration G over B here, right? But I will not continue here. Okay, and then you can spell pretty everywhere, anything here, and this is of course something monstrous, right? Elliptic cosmologies of elliptic configuration space here, right? But on the other hand, it is quite available, I believe, not only to some people in this room, right? Doable, right? But it can take time, of course, right, to understand what is it. With elliptic cohomology, the approach is maybe not too mysterious. You replace Andrei's talk. He considered for cohomology polynomials, invariant, double invariant polynomials, K theory, Laurent polynomials, double invariant polynomials, and elliptic level is Laienha polynomials or invariant Laienha polynomials. And there are some axioms due to Kapranov, some other people, you know, right? Axioms which pretty much, for simple example, pretty much sufficient to extend the theory, at least to know the expected answer. Okay, so this is definitely this expected answer, right? And moreover, there are some papers for in particular examples when it is checked. Okay, perfect. So this is what I was going to say. And then what are elliptic Hall polynomials? The last. Anyway. So here we are, right? It works now. Just standard definitions. Here we have what I consider the key Daha formula. This is exactly Q McDonald meta. Right? Let's read it together. You integrate Gaussian, right? Gaussian with minus to ensure the convergence here. Any function f, reasonable function, then you multiply it by Macdonald's polynomial with symmetric setting, normalized as such. They are called spherical Macdonald polynomials here, and the claim is that you will get f x at lambda plus rho. So shift by lambda can be provided by integration. Integration with P lambda here. If you think a little bit, this is pretty much meta formula, but meta formula with some kind of identity, but you with Bessel's. So what is the main formula from classical analysis? Bessel by Bessel time Gaussian, integrate with measure x to 2k here, you will get the first p of this of mu, p of mu. Bessel lambda, Bessel mu, integrate with the Gaussian. The measure is, of course, must be classical Bessel, x to 2k here. The answer will be j of lambda evaluated at mu. This is absolutely the main formula in Fourier analysis of Bessel functions. This is pretty much the same formula. Okay, so what are elliptic Hall polynomials? So first of all, I need to induce Jackson integration, which is simple. You need some invariant function. Of course, invariant function can be only like this. Summation over all affine while group. Over the lattice, if the function is invariant, and over the lattice. Jackson integral, just summation. Instead of creation, you have summation. So what is elliptic Hall polynomial? In what we discussed before, including this particular formula, replace integration, image integration, by Jackson summation. You will get exactly definition of elliptic Hall. Sasha is not present, Braverman, but there was a nice paper here, Braverman, Kashdan, and Manish Patyak, if I remember correctly here. They try to introduce double p-adic group here. Anyway, interesting story here. But anyway, elliptic. But first of all, of course, let me mention Kapranov, at least Kapranov in this business. So this is definition, guys. Daha's attack isomorphism. The number of elliptic Hall polynomials coincides with the number of Kac-Moody characters of level L. Exactly. because of some periodicity. But anyway, not many lambda potentially there are infinitely many of them, but you don't need so many, right? You need exactly the number which is equals to the level L here. Okay, so elliptic Hall polynomials. Let me, what is the place of elliptic Hall polynomials in this picture? This I can explain to you. You go to this level. At this level, you will get elliptic Macdonald polynomials, a little bit unpleasant, I must say, right? And then this is when you kill one of the parameters. Then you will get elliptic Hall polynomials, so somehow transitional here and here. Okay, perfect. Oh, by the way, concerning this particular one, about 5-6 years ago, I found a paper because I was a referee. The paper found me, to be more exact, when they suggested absolutely reasonable approach to this particular problem. Basically, for not only for specialists or not only for specialists, for those who are interested and want to continue, basically, instead of series, they consider values, functions as values at some special points. This worked in their paper. I immediately understood the potential, but didn't do anything actually, right? But still, there exists a paper, right? Practically unknown, but I know I know this, right? When there is some very good remedy, how to manage this particular guy. Forget about series, consider values. Values are some special points here. Then you can manage it, right? Then there will be no convergence problem. For instance, they defined in the same way Macdonald polynomials, right? As functions at some special sets of points. Somehow connected with Andrei did long ago here with Grisha Alshansky about interpolation polynomials. Interpolation polynomials, by definition, means functions as some sets of points here. But anyway, good story here, and then presumably we have something else at roots of unity, but this is different. Okay, here we are, the definition of elliptic Hall polynomials. You see, elliptic Hall polynomials is literally what we are going to consider during the remaining 15 minutes here, but just for different choice of integration. And by the way, this Jackson integration is pretty much closely connected with what we did with sharp zeta functions when the contour was like this. Summation, anyway. So very good. Now we are approaching actually the end, right? Here we are, right? Now for arbitrary root systems, for any given reducible root system here, we come with this definition of Z plus. Z plus because we are deforming it a function. It, well, again. Okay, good. No, again it switched to does work. But anyway, I cannot use the cursor here. But and I'm not tall enough to reach the top. I am good, but not that good. Okay, so the first line, guys, definition, right? The denominator can be exactly calculated, some nice product formula, which is exactly Macdonald method, exactly. Good. Thank you. Okay, then let me introduce this letter S, right? And I'm going to calculate the limit. Right? How to calculate the limit? This is pure elementary and very simple calculation. I need just to calculate the number of positive roots, long and short. So statement, right? Just very simple. It is in the limit. It will be, for instance, you can ask, can we generalize zeta function to arbitrary system? Yes, you can using the same e to x squared, etc. here. This integral can be immediately calculated, reduced to one-dimensional integral. But you need to count the number of positive roots only, right? Because mu function contains products over positive roots. So this is short roots. This is about long roots, and n over 2 is just because dx. Dx now is vector, of course, right? So this is the formula, and the answer is like this, right? The limit nicely exists, and it is exactly eta function. Eta function, by definition, it is plus zeta function, 1 minus 2 to minus s, zeta of s here. S is, so what is s? It used to be sk plus 1/2, but now it is like this, right? Then surprise. Now we play with epsilon, right? Epsilon because of the same reason to improve the convergence of the integral. Later we'll do meromorphic continuations, but later. But can we just save this integral as much as possible? So now let's assume for the sake of simplicity k long equals k short, or simply AD. Fine. Then the claim is consider this particular guy rho divided by h, Coxeter number here. This is the best, the optimal. And then this integral will converge an analytic with nice properties here when real part of k is greater than minus 1 over h, right? Then surprise for me at least, right? You plug in, you will get the corresponding value of s. Look at an. Here I calculate for an here, right? For an, right? So this is exactly v or whatever. Let me call it v is Coxeter number here exactly. So v times v minus 1, literally the count of positive roots here. And then let's plug in minus 1 over v. Let's add the guy which is responsible for dx here, and you will get 0. Perfect. So this integral, as we already observed, is well defined, analytic, convergent, everything, right, within the whole critical strip here. So if you wish, it is the second, the third, the fifth alternate definition of the Coxeter number. So this is exactly how Coxeter number appear, right? Coxeter number is the value of k. Look at this particular guy here, the value of k, such that s is 0 here. Definition, right? But for me, it was a little surprise here. So you see, I decided to show you this calculation, trivial calculation in full detail. So you calculate here, right, and then again, eventually you will get 0. So perfect, right? We cover the whole string here, and then immediately there is some suggestion to use it for Kuehl-Lindelöf conjecture. What is the Lindelöf conjecture? Very approximately, that the behavior of zeta function in the critical strip is pretty much the same as apart from critical strip, right? Grows, but very, very slowly, actually, right? Like t to whatever, I will skip the definition. So here we have the integral which does not distinguish between critical strip and something to the right, right? Perfect. So if you have any estimates of this particular stuff, then you have some qualitative suggestion. But I have something better than this a bit later here. Then you have some qualitative at least suggestion, right? How to approach Lindelöf, because we have the theory which doesn't distinguish when critical strip is nothing. There is no critical strip actually, right? Integral representation works. Okay, then the little calculation, but I need to do something explicit here about an, right? For an, v is n plus 1 Coxeter number here. Let's introduce this guy just technically. V circ equals minus kv here, right? Then you calculate s. Nice recalculation, right? Then I use this calculation, of course, below here. And then we have some interesting, strange duality. V goes to V naught. Look at this particular guy. So S, we have duality when V goes to V naught. And K, anyway, I will state it later. But right now we see that there is some duality between V, which is Coxeter number, and with something which is absolutely not Coxeter number. It is minus KV, negative whatever. But we have Deligne theory, we have Daha theory, we have super polynomials. It is GLT, according in Deligne's terminology. It is a story about GLT, when T can be arbitrary complex. Not GLN, but GLT here. But let me show you it is exactly what I already mentioned to you. So what exactly epsilon 1 to epsilon u duality here. Let me show it to you. Almost a theorem. So there is stabilization. This formula which we found actually depends only on Coxeter number, literally, right? The claim is that there is some triple function qt of course and a such that if you plug in t, if t is q to k, but this is standard for us, and if a is t to v, Coxeter number here, that these things becomes exactly the polynomial we considered before. Exactly. Anyway, it depends uniformly. It depends only on the Coxeter number. So we say that this triply graded generalization, QTA formula. Okay, and then theorem, but this is solid part. This is the existence of ZC requires little analysis here. The theorem is that we have superduality. Superduality here is T goes to Q minus 1. Here it is. T goes, Q goes to T minus 1, Q minus going to T. So it is very well known that it's pretty much the same as epsilon 1 goes to epsilon 2 for, in terms of Hilbert schemes of C2 and so on and so forth, right? So this is superduality. Of course, superduality is absolutely the key conclusion from Havana's theory, from the theory of superpolynomials, practically anywhere. Then you do the following. You substitute, right? And then you will see that this is exactly, this superduality, exactly V goes to V naught, exactly. Minus KV here. In the limit, it appeared that K goes to 1 over K, of course, because Q goes to T, T goes to K here, right? Then V goes to this particular. This is exactly the symmetry of the formula for zeta function. What could happen if there is no such symmetry here? Then we have a contradiction in mathematics, because we have some kind of connection between different values zeta function, which is impossible, of course, right? We know that these particular two different points must coincide in the limit. This is exactly what happens. So this is expected, but still nice straightforward calculation. And then almost the end of my talk here is now we have something interesting. Now we have new possibility. Instead of considering GL2, what is GL2? SL2. A equals T squared. What is SL3? A equals T cubed, and so on and so forth here, right? But it is much more reasonable. We know this from the theory of super polynomials, knot invariance, link invariance, and so on. Here we know very well it is much more reasonable to consider when A is 0, to consider some different track here. Here we are, right? So you have new possibilities, new potential, and still K goes to 1 OK, which is potential connection of big case and small case. This is another vision and much more realistic, I believe, approach to state, or to state maybe not exactly to prove the classical Lindelöf hypothesis, but to state at least Lindelöf hypothesis in this particular setting. Okay, another possibility, another new interesting story here, and then the end of the story that what we discussed analytically is actually directly connected with invariance of length spaces here. So what is a length space? Very easy to define. You have C2 with two coordinates with x and y, and x is subject to action of roots of unity, right? Then you can restrict it to the unit sphere here. You will get length space N1, which is non-trivial, of course. Okay, so this is what I suggest is connected with what Serezha Gukov called, or maybe not only him, Z hat, etc., etc. here. So this is the simplest example. When we have something which is expected, actually it is invariant, triply graded invariant of length spaces here. So here we begin with 1 over n to s. Eventually it appeared, after this long, very much analytic theory, appeared to be ln1, so entirely algebraic something. But in what sense? So anyway, before finishing my talk, still I have 5 minutes, right? Let me just realize the next page actually, but I prefer to make it like this. So some long story. Eventually it appeared that it is invariant, right? Some invariant super polynomial, right? Of length space here. Entirely so now it is entirely geometric, right? Exactly 1 divided by n. So we eliminated s first, right? Replaced it by some q, added q here, then t appeared, then a appeared. So this is pretty much the end of the story. Do we have a theory? We don't know much about triply graded invariance of length spaces. This is next level here. Of course, we know what to expect. They expected some nice modular, not exactly modular, more complicated than modular function. But anyway, they are serious. They are not polynomials. There is no question about it. Okay, so then geometric challenge is to find some kind of M, who knows, conifold, right? Such that there are special fibers like fixed points or whatever here, if we are aiming at localization in proper cohomology, such that we can just consider cohomology of this particular guy, can be complicated, who knows, right? Such that eventually you will get exactly this particular interpretation. So again, there is absolutely no problem with one particular guy, but the classical problem is that we consider summation of them, right? Do they appear in some manifolds? Of course, it is about length spaces are 3-dimensional. They can be embedded actually in 4-dimensional, but 5 dimensions is granted, of course. They can be embedded naturally, but are there some remarkable fibers, and can we use some kind of localization? Which cohomology? All these questions are, of course, open. Essentially, I'm done. Do I have anything to add? No. Let me go to the last page then, right? The first is more or less what I summarized. Sorry. Don't focus on the second. We'll discuss this juicy picture a bit later here. But first, something mathematical. What we really achieved, we did not somehow, instead of generalizing L functions, we created some kind of construction which modular Q functions, which are limits at t when t goes to infinity, with L functions, right? So we have something when the first arrow, which is the limit q to 1, which we discussed actually, seriously discussed, goes to L functions, directly L functions, and the second limit, which I discussed only vaguely, when t goes to infinity, then it will be modular functions. So here we combine two theories in one. Of course, everyone understands that there can be some Milin transform, but this is well beyond what we see in this picture. Okay, so this is exactly some kind of unification, not exactly deformation of zeta function, not exactly deformation of modular function, but unification. And we sacrifice modular equation, we sacrifice s to 1 minus s here. Instead, we have something else, something very interesting. And then this is a smart way just to show you what we are doing here. So smart way to present Riemann hypothesis, any kind of Riemann hypothesis, but in our business is Q. So what do we have here? So here we have real direction. So here we have imaginary direction. And then I borrowed it from some classical papers here, how to present, how to visualize that there are no zeros of something in this business. It is this is exactly our zeta q. In the right have this is imaginary zeta q here. In the right half plane here. So suggestion, well known to specialists, I believe, is to consider the following: consider the real part multiplied by the imaginary part, right? Then, if there is some zero, you will immediately see the cross, very absolutely obvious cross here, right? There are no crosses, and the picture is reasonably smooth. And then, according to what I see, I'm done. Yeah, am I right? I still have 5 minutes. Okay, I'm done.
Yeah, thank you. Well, let's thank the speaker. Questions, please. Questions. I have a question. I have not caught explicitly whether each zeta function can be extended to the right of the strip or a half plane it is defined at.
Yes, in this business always, their Miramorsk continuation is more or less goes through total pole decomposition. In Q calculus, always you can use Cauchy theorem, right? This is more or less what I'm doing, right? And then it's not a problem at all. It is, technically, the answer is that there is classical Hermann Weyl, Arthur, Heckman, Obdam, how to say, picking up the residues technique. This is what I'm employing here, right? Analytic conditions are Miramorsk conditions. But I claim that we have nice behavior of the integral themselves, which is can be some optimism, at least for specialists, right? Concerning Lindelöf or whatever.
Okay, more questions? Please. Yeah.
Sorry. So by that graph. Yeah, so. Conditionally, Nikita can say more here, but still, potentially, Nikita will discuss parallelism between gauge theory and between quantum many-body theory in his lectures here, right? So the last destination is elliptic quantum many-body, which is, so to say, elementary. It can be discussed. Divergent, but still, he exists, you know, right? And then it is up to Nikita to explain which kind of physics d equals 6 whatever theory, right? Which is exactly, and this is presumably this is the last integrable theory, period, right? Whatever we are doing, we cannot go beyond this with one reservation. At truth of unity, there is one more step here, and who knows what happens to truth of unity? You have four epsilon 1, epsilon 2. You mean?
If you remember, we discussed with you in Stony Brook.
But in non-integrable, right? We failed. We tried to. You mean integrability? Oh,
yes,
well,
yes,
there are some other things.
No, there are things which are not related to elliptic curve. You can, I mean, there are simple things which you can define over the rational curve, and then you have many parameters.
Not very many, but still,
I
know about 4 epsilon, some other parameters. They will not
live to the double elliptic system. Definitely not.
Yes, there are some remarkable identities, absolutely true, right? But concerning the what is integrability naively? Fourier transform, nice theory of Fourier transform. This is integrability, right? But anyway, this now it will be his part of the story. He will answer all your questions.
Okay.
Thank you. Yes, please. TT, trigonometric. Quantum many-body problem. Yeah.
Problem.
sorry, guys. QMBP. Right?
Okay, I'm afraid we have to stop here, and how we will attend the next
Sasha,
talk.
Braverman, right?
Yes, there is a quick announcement that Sasha Braverman's talk will be online. He wasn't able to come, and we'll make a switch in a minute.
Спасибо за помощь. Что-то я...
Sasha, are you here?
Yes.
Yeah, we can see you.
Right, share screen.
Could you try to share your screen? Nice, we
So
can
do we
see you.
start? Can we start?
Could you say something?
Саша, слышно?
Can you hear me?
Вас не слышно, Саша.
Can you hear me now?
Теперь слышно. Okay. Our next speaker is Alexander Braverman, who will talk about an introduction to symplectic duality and Coulomb branches of 3D quantum field theories. Please, Sasha.
Okay, thank you very much. So first of all, I would like to apologize that I'm not giving this talk in person. So I was really planning to be there for this week, but for some unforeseen circumstances because of which I couldn't come. I decided to slightly change the structure of my talk compared to what I originally announced. So, well, the idea was this is, as Anton told me, this is primarily supposed to be aimed at, you know, students and young people. So I wanted to give some kind of survey, but I wanted to maybe slightly shift the emphasis of the survey. So maybe let me say briefly what will be the structure of the talk. I want to kind of connect it eventually with some other lectures at the workshop. Namely, so basically I want to first give a survey of my work with Finkelberg and Nakajima and maybe other people about the Coulomb branches of 3D gauge theories. I need to tell you right away, you don't need to know anything, any words from physics. I'm going to actually give mathematical definitions of whatever I'm going to talk about. And second, then I want to switch to discussing similar subject, switch to discussion of 4D gauge theories. And here, well, there will be some constructions and results, but also there will be in the end what I want to try to get to in the end. I want to get to an open problem, and so I'll say in the end what the open problem is. So an open problem will be about constructing something, and here I want to connect to actually lectures of both Antonov and Nekrasov. So some kind of, so here you can view everything I'm going to talk about as some kind of very mathematical. You can view it as a very bizarre way in some to construct geometrically a lot of different integrable systems. And so here, when we get to the solving problem, so this will be about possible way to construct, let's say, a lot of quotation marks integrable system of Hitchin type. But that will be something which is not done. But before I get to that, I hope that I will have time to get to that. By the way, I have a question. Do you have 60 minutes or oh?
Yes, you have 60 minutes.
Okay. All right. So let me start. So we start with some very elementary mathematical data. And maybe we'll start with some group G, which, so again, the motivation sort of comes from physics, but in physics, people work with somewhat analytic objects, for example, compact Lie groups and so on. So I want to be completely algebraic, so I'm going to start with G, which will be a complex, reductive, maybe connected algebraic group. And I start with something which was historical reason I denote by capital N, which is just a fine dimensional representation of G. And then, so the physics tells us to this data, you can attach some kind of structure, and the structure you can attach to it, which is relevant for me at the moment, is something which is called 3D, three-dimensional, n equal 4. Well, that's a different n. Let me write it like this: n equal 4. This n is the amount of supersymmetry, gauge quantum, let's say, gauge theory. And whatever this thing is, well, we as mathematicians don't really know what these words mean, but we can only study some mathematical objects which we believe can be attached to the structure. And so the mathematical object which maybe is possible to define is something which is called the modular space of vector of this theory, which is by itself a very complicated object, so I don't really know how to describe it, but it has some special pieces which apparently do have mathematical definition. And so, so to this we attach to such data, we attach something which is called Higgs and Coulomb branches of the modular space of vector. Now, so now I want to sort of forget about words from physics. So what kind of objects should those be? Now, physicists tell us the following, which is kind of not completely precise. So physics tells us this. So I'll denote this by M sub H and M sub C. And so what these things are supposed to be, they're supposed to be hyperkähler. Well, what we can put in quotation marks. Hyperkähler manifolds. Maybe with some additional structure. And I'll talk actually about what additional structure, what kind of additional structure you might want to construct there. So now already here I want to say that why they put hyperkähler manifolds in quotation marks is that because typically these things are going to be singular. Often singular, and so since it's not completely clear what we should call singular hyperkähler manifold, so therefore mathematically it's this hypercalus structure is something that I'm not going to really talk about, but I'm going to kind of fix some particular complex structure there. And so, so if one fixes a complex structure, then it turns out that one can actually make things algebraic. So kind of slightly different point of view. In fact, they can be defined, again, choosing particular complex structure. Both of these can be defined as affine algebraic varieties. As I said, possibly singular, which are in fact Poisson varieties, should have Poisson structure, and generically symplectic. So it means that this Poisson structure, in fact, on the smooth locus of this variety, it comes from symplectic structure. I'll give examples in a moment. And so the question is, so question number one for us, and I haven't yet gotten to integrable systems, but there will be integrable systems very soon. Question one, so what is their mathematical definition? So somehow some kind of physics tells us that such objects should exist. And what are they mathematically? And so let me stress that we start with some very simple algebra, very simple mathematical data, just a group and the representation. And so now for M Higgs, there is a very simple definition. Well, especially if you don't bother about some details, namely, it's the following thing. So what we do is we take the cotangent bundle to our representation, which is just nothing else but just this representation plus its dual. I should say that by actually secretly from, if you look at this physics definition, that everything should only depend on n plus n star. So for in particular, this, if you replace n by n star, you get the same answer. And this will be apparent for the Higgs branch, but much less apparent for the Coulomb branch. And then so if you take this thing, well, okay, let me write the formula, and then so then I take the used to denote it with 3 bars, the Hamiltonian reduction of this by G. So what does it mean? So this T star n, this is just, well, it's a vector space, but it's a symplectic vector space endowed with the symplectic or Hamiltonian action of G. So it has a moment map, which goes to the dual space of Lie algebra. And so M Higgs is mu inverse of 0 quotient by G. Now, of course, because this is usually going to be Navier reaction of G, you have to be careful about what you mean by taking quotient. But here, I want this to be an affine algebraic variety, so I'm going to take the most naive notion of quotient possible, namely, so this is an affine variety, so this thing is a spec of the following thing. I take this pre-image of 0 under the moment map, take C of that means an algebra function, so that then take G invariant function. So this is an example. Well, this is the definition, if you want, of this Higgs branch. And a lot of, so this is some class of groups and representations which are called, where you get something which might be familiar to some people for other reasons, namely, let me say it here. So, for example, all Nakajima-Weaver varieties are special examples of this construction. Namely, those correspond to what's called Weaver gauge theories. And this is the following thing. So suppose that, let's take Q, which is a graph. And let me actually choose an orientation. In fact, at the end of the day, nothing will depend on the orientation, but let me choose an orientation of the graph. And so, well, okay, so we have some kind of graph here with orientation. And then what I want to do, I want to attach some vectors. So to every vertex, I, which is a vertex, I want to attach two vector spaces. Find everything, find dimensional vi, wi. This is just vector spaces. And then I did take the following thing. I take the group G to be the product of GL vi. And I take the representation N to be the following. It's a product over all I. First of all, let me say product over all edges. I goes to J, form from Vi to V, to Vj times product over all I, form from Vi to W. Now, if you take, well, that's a kind of, if you just think about groups and representations, this looks like a very not the first example you would think about, but this is a word. This is what sort of Kuvers give you, and if you run this Hamiltonian reduction construction, this definition of the Higgs branch, in this case, you get, by definition, you get what's called Nakajima covariety. So Nakajima covariety, so MH in this case is called Nakajima covariety by definition. And of course, Nakajima started those in great detail. He related them to representations of Kazhmoudi algebras and so on, which is not something I'm going to do because I don't have time. But and maybe examples include things like for example, if you take C2 mod gamma, where gamma inside SL2 C is a finite subgroup, then these things are of this type. And other examples, another maybe type of examples is that if you take, suppose that you take the Lie algebra SLM, or complex numbers, inside here take N, which is nilpotent cone. And this nilpotent cone is a disjoint union of nilpotent orbits, what we call O lambda, and lambda by some kind of partitions in this case. So this is just, they're numbered by partitions of the number N. And then for every lambda and mu such that O mu lies at the closure of lambda, there's a notion of transversal slice, which is called Slotoway slice, so I'll call it S lambda mu. This is Slotoway. This is some particular choice of a transversal slice to O mu inside the closure of O lambda. And this is also an Nakajima covariety. And there are many more examples. I mean, it doesn't have to be. I don't have to be in the context of the Nakajima covariaties, but just what I want to say that a lot of known symplectic varieties arise in this way. Now, okay, so this is the Higgs branch, and now question: what do we know about the Higgs? So question 2 is, what do we know about MC? And so let me, so MC is more difficult to define, and I want to, the main point of my circuit part is explain how how to define it, and then I want to go into some generalizations. But before I tell you how to define it, let me list some properties that this definition will have. And then I'll tell you how to invent a definition which satisfies those properties. Okay. Any questions before I proceed? Right. Properties of the definition to come. So property number one is what I already told you before, but I'll say it a little bit more precisely, that MC is an affine normal Poisson generically symplectic. Well, let me just write generically symplectic. Let me write in quotation marks symplectic. So it means that it's kind of as symplectic as possible. So for example, if it's smooth, then I want it to be really symplectic. And this, for example, I want to be the whole smooth locus to be symplectic. And actually is of dimension. Dimension turns out to be independent of the representation, twice rankage. Second, and this is already is going to be related to something I mentioned at the very beginning, MC is going to be endowed with a canonical integrable system, and the integrable system, so there will be some map, what we call it phi, and the base of this integrable system will be will always be the same. So it will be, well, let me write it like this. So here I choose T inside G. This is a maximal torus. This T is its Lie algebra, and W is the Weyl group. And so there will be some map like this, which is a completely integrable system. So it means that the fibers of this map are Lagrangian subvarieties. In fact, generic fiber will be, well, I mean, usually when you have an integrable system, classical integrable system, you want generic of this fiber, you want to be torus in some sense. Now, the word torus in mathematics means a lot of different things. So if you're doing a real manifold, then torus is a circle to some power. If you're doing affine algebraic geometry, then a torus means that it will be just C star to the power, in this case, rank of G. And later on, when I get, if I have enough time, when I get to this open problem part that I mentioned, then it will become more interesting because I promised to say something about integrable systems of Hitchin type, and there will be conjectural, there will be some similar construction where the fibers will be some abelian varieties. Generic fibers will be abelian varieties. Okay, so that's structure number 2. Structure number 3 is that MC will come with a special, with a canonical C star action. With respect to which, so it means that its algebra of functions has a canonical grading, with respect to which the Poisson structure has degree -2. In other words, if you think about symplectic varieties, that means that we have a C star action, so the dial is the symplectic form with weight 2. 4 is that everything here will actually come with the canonical quantization. Canonical. Of these structures. So it means that so if we let AC be the algebra of functions, almost thing, which is supposed to be Poisson algebra, and we have an integral system, so it's endowed with some special, sufficiently large Poisson commutative subalgebra, then there is a deformation of this, depending on parameter h bar, which is already, well, non-commutative deformation, inducing the corresponding Poisson structure deformation, and everything here deforms. For example, integral system deforms. So that's structure number 4, and maybe last structure I'm going to mention before we talk about it. So I want to mention a few examples, and then I want to talk a little bit about the construction. There's something which thesis called flavor symmetry. Namely, suppose that there is another reductive group. So assume that we have some group G sub F. F stands, the letter F stands for the word flavor. This is what thesis called flavor symmetry, which sits inside the automorphism group of our representation. So suppose that we have something that our representation is not irreducible, for example, and we have something bigger acting on this representation. Well, actually, sometimes even for reducible representations, you can have this because for reducible representation you have just C star, which dilates everything, which sits inside the automorphism group. Then all of the above has a, well, has means canonically given. Has a deformation over the following base. So we take T sub F. So T sub F means, again, the Lie algebra of the maximal torus for this flavor group. Modulo WF, so which is the Duval group over the flavor group. You can also think about this as G sub F modular adjoint tension. So that's kind of the structure we want to, we're after. Let me give you one. So I should say that, again, I want to stress what I have already stressed, that we start with an extremely simple mathematical data, like something which people in the 19th century were working with. So just have a kind of reductive group, for example, GLN or something like this, and we find the mass representation. For example, the representation can be 0. That's a pretty interesting case already. And then we're going to sort of attach this kind of relatively rich mathematical structure to that. And now I should say that when we take a sufficiently general group G and kind of sufficiently general representation, then it doesn't make sense to ask what we get, in the sense that we get some varieties which sort of have never appeared before. So only some very rare cases we might present an answer to what the Coulomb branches are in explicit terms, because explicit terms, by definition, mathematics means that you can describing it in terms of something that existed before. And so in most cases, these are not varieties which have ever appeared before. But in some cases, they are familiar varieties. So let me give an example. So there are very few examples which work where I can say something for arbitrary group. For example, you can do the following. Suppose that take any G and take this M to be the Lie algebra, so this adjoint representation. Because G is reductive, adjoint representation is the same as quadjoint representation. In this case, we can actually describe this thing explicitly. And so, this is a very simple answer which I'm going to present, but it's the only case when we have a really simple answer. Namely, in this case, this MC is going to be the following thing. So we take this maximal torus, then we take the dual torus. So for every torus, there's a canonical dual torus, so such that its character lattice is the core character lattice of the original torus. Then I'm going to write the following. So in this whole business, I always have a huge notational problem because I want to take cotangent bundle to the torus. And so if you denote torus by T, then when you write cotangent bundle, it looks awkward. But so maybe you can say that you should denote, I mean, the standard notation for a maximal torus of reductive group is H. But H is not good either because very soon we're going to consider some cohomology everywhere. And so H in notation H is going to interfere with cohomology. I think this problem is unresolvable. So let me just write it like this. But here, the meaning of the two T's is different. So one T stands for the torus, the other T stands for the cotangent bundles. And then, on the torus, we have the action of the Weil group. So we have the action of the Weil group on the whole cotangent bundle. So we just take the quotient by double. And note that this cotangent bundle to the torus, it's nothing else but this torus times the dual space to its Lie algebra. And the dual torus is defined in such a way that the dual space to its Lie algebra is more or less by definition the Lie algebra of our region. So this thing looks like this. So before we take the quotient to the by the Weil group, this thing has a canonical map to T. And then when we mod out by the Weil group, this obviously has a map to T mod W. So that's our integral system. So that's a very, well, that's actually, this is a very important case, but that's kind of a really simple case. And that's the only case when we can, where we can sort of describe things in very simple terms and kind of uniformly independently of G. Then there will be some examples which I'm going to present a little later for some specific choices of G and M. There will be some interesting answers. Okay, any questions so far? Okay, so if there are no questions, let me maybe let me give you another uniform example. But that example is going to be it looks like it should be simpler than this, but in fact it's more complicated, at least in terms of the answer. Namely, again, take any G and take this representation M to be 0. In the physics language, this is called pure gauge theory. So in fact, this representation M, this is really closely related to the matter in this gauge theory, and when it's 0, this is what's called pure gauge theory. Then what is the answer here? The answer here is something, let me describe it, something which is called the universal centralizer. So I'm going to describe it as a variety. By the way, it's not something, in the previous example, something which I forgot to say it, but it's kind of clear that this thing is more or less symplectic. So the cotangent bundle to torus is symplectic on the nodes because cotangent bundle to everything is symplectic, and then we just mod out by some finite group. In fact, we mod out this finite group forget something singular, but it's clear that this action of this W preserves the symplectic structure. So when we without by W, at least we get a Poisson variety. It's clear that generically is going to be symplectic. So in this example, I'm going to present the variety and this integrable system, but the symplectic, in fact, in this case, the variety will be smooth. So in fact, it will be just a symplectic variety, but the symplectic function will not be apparent from the construction I'm going to present. So to have a symplectic structure, to define a symplectic structure, you need a different presentation of it, different construction of it, which I won't talk about. So I'm not going to. So I'm going to try to tell you what the variety is, but I'm not going to tell you how to define a symplectic structure. But the claim is that it does carry canonical symplectic structure. Namely, this thing is the following. It's kind of the modular space of the following data. So you can see the pairs. X in G. Let me put G star, but that doesn't matter. I mean, of course, G and G star are isomorphic, but it's kind of more canonical to write it in G star. And here I put reg. Reg means it's a regular element. So regular element, for example, if you think about the group GLM, then G or G star, this is just n by n matrices, and regular element. It means it's a regular matrix. It means that that's characteristic polynomial is equal to its minimal polynomial. Or a general definition of regular means that its centralizer in the group is of minimal possible dimension, which is equal to the rank. And so we take pair X, which is a regular element, and G in G such that these things commute. And then we went out by conjugation. So, well, as usual, when you can see the quotient, you have to sort of work a little bit to make sense of this, but in this case, it's actually not a big problem. So, this is a variety. So this is going to be our variety. So what is our map pi? In this case, our map pi in this case is going to be the following. It's sort of only, well, kind of, well, it goes to oh, oops, sorry. There's something sorry. There's something I'm doing wrong here. So here I need to. I forgot I have to do it for the dual group. So here, maybe let me write here. So when I start with this group G, there's another group you can attach to G, and it's called the group G check, and this is the Lagrange dual group. And it's characterized by the condition that, well, one way to describe it is to say that a reductive group corresponds to some root datum. And so G check has root datum dual to that of G. So I forgot that here should do it this way. And so this goes to, so we should construct, we're going to construct a map to G check star reg mod G check, which is the same, actually, again, it's, if you look at the definition, it's canonically the same as our original T1W. And so this pi just sends this pair XG to X. So it only remembers the conjugacy class of X. So the modular space of regular conjugacy classes is the same as the modular space of all conjugacy classes. So it's kind of, if you think about the Lie algebra the group GLN and the algebra, which is just matrices, then we're just saying that this T mod W, this just remembers spectrum of a matrix, and we're saying that for every, basically the statement is that for every choice of spectrum, for every choice of eigenvalues, there's a unique conjugacy class of regular matrices with these eigenvalues. So that's, and then, well, let me maybe leave this as an exercise, but it's not a completely trivial exercise. Define a canonical symplectic structure. Let's call this thing capital Z, because Z stands for the centralizer, so this is called the universal centralizer. Define canonical symplectic structure on Z, so that pi is an integral system. So secretly, this integral system is closely related to what's called open Toda integral system, but I'm not going to comment on that now. Okay, so I have a question. When exactly am I supposed to finish? I mean, I know it's 60 minutes, but I think I started late, or am I supposed to finish exactly at 4 o'clock, or is it?
Sash, it's a bit flexible, so it would be nice if.
Okay, well, I don't want to go like terribly over time, but let me know what is the expectation.
The expectation is 4 o'clock, and if you go over like by 5 minutes, I think
okay, fine.
it'd be okay.
Okay, so let me give you, I'm not going to probably give you the details of the construction. So now let me talk about construction. I'm not going to give you details, so let me actually give you the actual construction for the n equal to 0 case. And then I'm going to say that there's a relatively easy way to generalize this to arbitrary n. Maybe I'll just mention the brief idea, but so construction. So let's take n equals 0. Then construction is the following. Well, after all, we want to construct some affine algebraic variety. So when we want to construct some affine algebraic variety, it basically means that we want to construct some algebra of functions on this affine algebraic variety. So we're after some algebra. Now the idea is that so in this case, I wanted to call this algebra AC. This algebra AC is going to be defined as homology of something. And I'll talk about what this something is. Now, already here, you might ask a question. So usually homology doesn't have an algebra structure, and cohomology has an algebra structure. But sometimes homology has an algebra structure. For example, if you take something like homology of a Lie group, then multiplication on a Lie group induces multiplication in homology. And this is kind of what's going to happen here. But to say these things precisely, we need to introduce something which is called the affine Grassmannian of the group G. Namely, let's introduce the following notation. Let's introduce the field K, which is just the field of Laurent power series in the variable T. And inside we have a subring O, which is the ring of Taylor series. And then we define the affine Grassmannian of G, which is some kind of infinite dimensional object, but not terribly infinite dimensional, which is just the quotient of G of K by G of O. Well, okay, the way it is written now, it's only written as a set, but we want to define some kind of object, an algebraic geometry. To define some algebraic geometry, well, the correct way to think about infinite dimensional objects in algebraic geometry is to define its function of points. To say what it means to map some affine scheme into that. I'm not going to do this, but somehow the claim is that this thing is what's called an in scheme. and in fact, it's int projective, so it's equal to direct limit of projective algebraic varieties. I'm actually cheating slightly here, so this is literally true if G is semi-simple. If G is semi-simple, it's reductive but not semi-simple, then things are slightly more complicated, but again, let me ignore that. So in fact, for every lambda, which is a dominant or weight of G, we can define some, there's in G of O orbits as some, I mean, actually, well, let me say it like this, sorry, let me say it slightly differently. So this affine Grassmannian, just first as a set, it's a union, disjoint union over lambda, which is a dominant co-weight of things of the, which I'll call lambda G. And so there's a G of O orbit. So if you try to classify G of O orbits on this affine Grassmannian, then the one corresponds to dominant co-weights. And then in appropriate topology, the closure of every such thing, this is a projective variety. And then you can now take the following thing. We can take, in this case, this AC is going to be, well, I want to take the homology of the affine Grassmannian, but in fact, I want to take the equivariant vector true-full homology of the affine Grassmannian. And so note that I can formally write it as homology. Well, if I use notations with algebraic stacks, then I can write it as a homology of the double quotient. And if I write it like this, then it's not inconceivable that this homology is going to have an algebra structure, because I said that if you take just a group, then homology of a group is going to have an algebra structure. And the algebra structure is induced by the multiplication of the group. And the same is true that if you take a group and a subgroup, if you consider homology of this double quotient, which you can define as homology of one-sided quotient equivariant with respect to the action of the other side, then the same multiplication in the group is going to induce algebra structure here. Now, what is not completely obvious, but true in general, there's no reason to think about to expect that homology is commutative. But lemma that says that in this case, AC is commutative. So that's kind of the definition for n equals 0 case, for the pure gauge theory. And for general n, one can define a similar space, which we call RGN. This is some space which maps to the affine Grassmannian. Well, in fact, I can even tell you what the space is. So namely, it's so this RGN consists of pairs G in G of K, well, G of O, and let's say M in M of O, such that G of M again lies on N of O. This makes sense. I can give a more dramatic description of it, but unfortunately I don't have time. But the point is that this, at least this formula makes sense, because obviously this condition G of N lies on N of O, it sorry, let me actually write G inverse of this. So if I write it like this, then the point is that if I multiply G by G of O on the left, then G inverse is multiplied by G of O on the, sorry, if I multiply G by G of O on the right, then G inverse is multiplied on the left. And then this condition that G inverse of N is N of O is doesn't change. So this is some space I can forget about this M, and then this kind of naturally projects the fine Grassmannian. Well, and then this AC in this case is, unfortunately, I need one more ingredient, which I'm going to hide the definition under the rug, and this is, I need to call something which is called Borel-Moore homology of the space, equivariant with respect to G of O. The space is slightly infinite dimensional, so you have to work a little bit by what you mean with what you mean by Borel-Moore homology, but it's not difficult. This is done. In our papers of this RGN, and this is and again the same type of convolution, sort of induced by multiplication in the group, will also make sense here. So this thing will be a commutative function. Now, I should say that this definition, if you sort of read the physics literature, then this definition is not as crazy as they think, because in physics, physicists tell you that functions on the Coulomb branch are given by some kind of monopole operators. And if you sort of try to understand what physicists mean by monopole operators, then it's kind of not very difficult to convince yourself that these monopole operators are precisely homology classes of such a space. So this is Borel-Moore homology again. If you don't know what this is, then just I'll say that's it is some version of homology, which is for compact spaces it's the same as ordinary homology, but so for non-compact spaces it's something slightly different. And so that's kind of the definition. And so the idea is that non-commutative deformation comes from the following thing. So let me explain the non-commutative deformation. It's the following thing. So we should consider the same homology of the same space. But now we should consider its equivariant with respect to a little bit more than this. There's another C star acting on the whole thing, which is called loop rotation. So this C star is what's called loop rotation. So let me do it in the case when n is equal to 0. So when n is equal to 0, then this RGN was just the affine Grassmannian, G of K was G of O. And so C star just rotates the variable T. And so, well, I don't have time to explain the details, but the idea is that when we do this, so I said that there was a lemma that this convolution algebra, that this homology algebra is commutative. So we actually have to prove this lemma somehow, but it turns out that the proof doesn't work if we introduce this additional equivariance with respect to loop rotation. And so when we start to loop rotation, then everything becomes a module over the equivariant homology of a point with respect to C star, which is the algebra of polynomials in one variable. So this is algebra over equivariant homology of a point with respect to C star, which is algebra of polynomials in one variable, which I want to call H bar. And so, and this H bar turns out to be the Planck constant in the sense that it defines the non-commutative deformation. And the last thing I'm going to say about the general construction is that this integrable system is the following thing. So if I take this, well, again, whenever I take this, well, kind of homology, Borel-Moore homology, cohomology, doesn't matter, of anything. So this contains inside, well, there's some unit, it's a module over equivariant homology of a point, because there's some unit homology class here, then, and this is an algebra. In fact, it's an algebra over, so this thing contains equivariant homology of a point with respect to G of O. And G of O, if you think about it, well, when it started as some kind of equivalent homology, cohomology with respect to some group, then the answer only depends on the homotopy class of it. And then homotopically, this G is this G of O is the same as G. That's easy to see. So G of O is kind of infinite dimensional, but the whole infinite dimensional part of it is something contractible. So homotopically, it's the same as G. And so this thing is the same as equivalent homology of points back to G, and that thing is the same as the algebra of functions on what we call T mod W. That's so. Therefore, this algebra contains this C of T mod W, and from the definition of my non-commutative deformation, it's kind of and so I told you how to define non-commutative deformation. This non-commutative deformation defines. This non-commutative deformation defines a Poisson structure, and it's an easy exercise from what I said that these elements, this function on T mod W, the Poisson commute. Okay, so I'm close to the finish. So now let me spend just a few minutes talking about some generalization of this. Any questions before that? Okay, so
I believe you can have a few minutes.
Okay, generalization to 4D gauge theories. Let me say 4D, and we go to supersymmetric gauge theories. Now, the idea is that, so again, if we believe in some words coming from physics, then we said that somehow when we start with a group and a representation, we can associate some quantum gauge theory to that thing, or some three-dimensional quantum gauge theory. And so, by the way, here, well, if it's three-dimensional, we can sort of put it on a free manifold. And in the whole previous discussion, this free manifold was just R3. And so, and now now the claim is that the same data actually defines some four-dimensional gauge theory. Now, if you actually look at physics literature, then physicists will tell you that in order for what they call physical theory to exist, there's some very strong condition on this M has to be satisfied. So, for example, if G is a torus, only the zero representation will work. But actually, I'm going to ignore that. So somehow the point is that if you want to define some analytical objects which require some convergence, something like hyperkähler metric or things like this, then you really need this physical theory to exist. If you want to if you only care about algebra, then essentially you don't need this physical theory to exist. As for example, you can make things work. You're supposed to be able to make things work for every G and M, for every group and N representation. And so, but so we, and formally speaking, we work on a form manifold which is R3 cross S1, some kind of four-dimensional cylinder. And in this case, this MC is again supposed to be hyperkähler manifold. Well, again, let me put in quotation marks because it's sometimes singular. Also, it will be truly hyperkähler only for some nice representations M, but for what I'm going to say, it won't matter. But it will be hyperkähler manifold of a very different type than before. Because before, well, in the 3D story, I only talked about this thing in one complex structure, but there was some reason for that. Namely, somehow this is some boring hyperkähler manifolds in the sense that they're going to look the same in all complex structures. And these hyperkähler manifolds, which correspond to 4D gauge theories, they will look differently in different complex structures. So for example, generically, for generic complex structure, they still will correspond to some affine algebraic variety. But in some special complex structure, they will not be affine anymore, but they will be projective over affine. And in fact, they will still carry an integrable system. And the integrable system, so in the generic complex structure, what will be the base of the integrable system? Generic complex structure. This thing will live over, this time, multiplicative version of what we had before. It will live over the actual group torus 1W. And so, and the special complex structure, this will, the base of the integral system will be the same. But the difference from what we had before is that now in the special complex structure, this is a projective. This is supposed to be projective morphism. And so here, well, let me put this generic here. Let me put this as P for special. So, and so I'll call this map by generic, and this map by special. And so, generic fiber of pi generic is still isomorphic to C star to the power rank of G. And generic fiber of pi special is supposed to be isomorphic to an abelian variety. And moreover, this abelian variety should vary when we vary the point in the base. You know, when we write C star, see the difference between a fine algebraic torus and kind of algebraic torus in the sense of abelian varieties is that all affine algebraic tori are isomorphic. And of course, not all abelian varieties are. And so the question is how to define these things now. Now, in the generic complex structure, there's an answer. So for MC generic, we do exactly the same as before, but we replace homology by K-theory. This is spec of K-theory geophore equivariant of the same space RGN. And then basically everything we can do, we do for homology makes sense for K-theory. If we introduce this loop rotation that defines an alternative deformation. And so this is just the kind of variant. So then we can compute examples, but at least the general definition is the same. For MC special, at the moment, there is no definition. And that was the open problem I want to talk about. So I want to say just 2 words what I want this definition to be, and then I will be done. At the moment, no definition. Although physicists, for example, Nikita computed a lot of examples. For example, they computed Nikita and computed the answer for all the Kuiper-Gauge theorems.
I believe we have to stop.
Okay, let me just say one last sentence. So what I want to say is that this thing is supposed to be projective over affine. So therefore, well, before we define just algebraic functions, and here this thing does have the algebra function, but this thing is supposed to be is supposed to have projective homogeneous coordinate ring because the fibers are supposed to come with the canonical projective embedding. And then sort of very vague conjecture, and this is what I want to say is an open problem, that homogeneous coordinate ring should be defined in the same way as in 3D, but replacing G by the corresponding affine cosmology group. So basically the slogan is that I want to think about 4D gauge theory as something like 3D gauge theory for the loop. And so I think it would be extremely interesting to make this precise. I can actually make this a little bit more precise than I said here, but I don't have time for that. But that's kind of the challenge in this theory. And so then last sentence I'm going to say is that this will be a way to define a lot of integrable systems of Hitch and type, because this MC in this special complex structure, the corresponding integrable system, they are kind of true integrable system with generic fibers being abelian varieties, and many examples that should be related to some kind of Hitch system. Okay, thank you very much, and sorry for going over time, and sorry again for
let's
not presenting.
thank the speaker. And we have 1 minute for short questions. Are there any questions? Sasha, the abelian varieties that arise as fibers, are they related to Jacobians of curves? Or
Well, in general, there should be no reason for them to be related to Jacobian, but somehow sometimes, yeah. For example, if you take this pure gauge theory, then you know many examples. You know what answer you want to get. For example, if you make pure gauge theory, then you're supposed to get what's called a fine Toda integrable system. And for example, in type A, the corresponding abelian varieties are exactly Jacobians of some curves, which are in this case called Seiberg-Witten curves. So this is the actually Seiberg and Witten, maybe Tanagi and Witten tell you that any 4D equal to gauge theory should be sort of controlled by some integrable system. And I think one of the purposes of Nikita's lectures are to describe these integrable systems. So this is exactly this integrable system. So the thing I'm after is kind of general definition of this integrable system. And what I presented before is that in some related but simple setups, we know kind of a very general definition. And I believe there should be a very general definition in this case too. But for this, we have to work with spaces which are more infinite dimensional than before, so to say. So therefore, I never try to sort of push this rule carefully. I can again say what I want more precisely than I just had time to do it here. But in principle, as far as I know, in this generality, there's no definition of this thing at the moment. But I think there should be. So there should be some kind of integral system of this type for any G and any representation.
I see one more question.
Okay, so I heard that before some physicists define the column branch as corrector varieties. So what's the relationship between this definition and that one?
Well, I mean, it will be something like character varieties in some very special case. So for some, it will be the case for quiver gauge theories for some very special quiver.
Okay, thank you.
But in general, they're not going to have anything to do with quiver varieties. And in general, the point is that they're not going to have to do with anything, in the sense that these are really genuinely new spaces which have never appeared before in any incarnation. So therefore, it doesn't make sense to ask how to describe them, because you have no language to describe them. So these are kind of really new things. But in some special cases, for example, if you take quiver gauge theories of, say, finite or affine type, you have a very explicit answer, and so in some other cases. But somehow the thing I want to do at the moment, in terms of this open problem, is to actually have a general definition in this special complex structure. And,
okay,
this is
let's thank the speaker once again.
Recording stopped.